Hey, everybody. Alrighty, we're going to go ahead and get rolling. We are still waiting on the GCP credentials, so we'll get those a little bit later when we actually get in to create our cluster and start messing around with things. So thanks for coming. I'm Zach. I work at Tetrate as one of the founding engineers here, and I worked as one of the early engineers on the Istio project at Google as well before leaving to join Tetrate. This slide is not fair at all because there are a ton of people that helped put this all together. A lot of them are in the room and are going to be helping y'all as you as you hit problems or anything as we go through this. So as we go through this, we'll be split up into two sections. We will have slides that we go through that I'll talk through that provide background content, and then we'll cut over to some actual code examples that are in a GitHub repo where we can actually interact with the real system and kind of see, use Istio to do things. Alrighty, and with that, here is our rough schedule. So we're starting just a touch later than we had wanted to, but we'll push right on through. So let's get going. So in this first section, what we're going to do, and we'll take some small breaks between these sections, right? So in this first section, what we're going to do is talk about Istio itself, the architecture of the system, and why it can do the things that it can do, and how that works. Then we'll actually go and set up a Kubernetes cluster, deploy Istio into it, deploy our demo app, and then from there we'll dive into each of Istio's kind of pillars and look at individual features and how we use those features. So in my opinion, one of the best ways to understand systems and why we built things the way that they're built is to understand the problem that they were built to solve, right? That is the critical context for the solution. So this is the problem statement that motivates Istio, right? As we take our legacy infrastructure that was monoliths, or maybe it is services, deployed into environments that really don't change very much, we have a bunch of problems, right? And maybe the biggest thing behind this move to distributed architectures is the desire for developer velocity, right? So I want my developers to be able to do more things faster because that's the gate for a lot of my business. So I want to decouple the teams from each other so that they can move independently and go fast, right? It sounds great, and it is great. But we have some problems. The tooling that we have today does not cope well with this new world, where things are dynamic and communicate over the network. And so when I talk about a modern distributed architecture, specifically what I'm talking about are service-based architectures, probably in containers. Doesn't have to be, actually. They're deployed into environments that are more dynamic than we have traditionally dealt with. If we think of Kubernetes, pods come and go and change IP addresses and change ports dynamically on the fly all the time. This is in direct contrast to some of the old like VM-based systems that we work with, where I can deploy a VM with a persistent IP address that runs one application for years, right? And maybe the most important difference in applications is the increase in the importance of the network, right? As we break apart monoliths into separate pieces, those separate pieces are composed over the network. And so we have to deal with the network in places where we never had to deal with it before. Procedure calls become remote procedure calls, and remote procedure calls have so many different failure modes that a normal procedure call on one machine never had, that it's staggering, right? And our tooling just really can't cope with it. And this is a lot of the problem that we see as we move to these service-oriented architectures. So Istio was built to solve these. And critically, Istio helps us monitor, connect, manage, and secure services. So let's dig into those. So when we talk about monitoring services, we really mean getting some visibility into the state of our dynamic system. And there's three key ways that we do that today as an industry. We generate metrics about our service, right? So as requests come in and go out, I want to publish metrics that some other system can consume that's a summary of that, right? How many requests did I 500? How many requests did I return 200, et cetera? I want detailed logs, right? So those metrics give me a great view of the front door of the application, right? What's going in and out. But they don't give me a lot of insight unless I've gone through and instrumented my code about what's actually happening. And that's where we traditionally use logging to fill in those gaps, right? How many of us have done print line debugging, and then that goes into production, and those print lines are still there, and we're still debugging with them later, all the time. And then finally, tracing, which in my mind, which is maybe the newest of these three from the perspective of monitoring systems that we're building, right? Tracing is kind of the new kid on the block, relatively speaking. And it's kind of like logs on steroids almost, right? So rather than just printing statements as I go through, I can actually annotate this object that traverses through not just my service, but if our system is set up correctly, we can actually propagate these traces through an entire set of services so I can see for one request that a user made, what happened through the 20 services that we had to go through to answer that request, right? It's powerful. And one of the benefits that we'll see over time as these systems mature and develop is better correlation capability. So that is the key piece that's missing today. And when you go hear people talk about observability, a lot of the hot topic now is events. And the idea of an event is that it captures these things together in a unit so that I can start to correlate metrics with logs, with traces, so that I can see for that slow request, why was it slow? What were the vital stats for my server? We want to connect services together, right? So just by show of hands, how many people have written a retry loop around an RPC? And it was a for loop, right? Like 1 to 3, redo it, yeah? How many have written one of those and then caused an outage because of that? I have. It's really, really easy to DDoS internal infrastructure when you can deploy like a couple mini machines at a time and then you have a for loop there. And this is really the problem. So if we look at when we first started to build programs that were communicating with each other, we had a set of problems that we had to solve. We had to solve naming. We had to solve delivery, making sure that the other end actually got the message that we sent. We had to congestion control. I need to not overwhelm the other server. We had to do all these things. And we saw these start to be repeated in applications that needed to communicate with each other. And so eventually we extracted that out into what we call the OSI network model. And that is the interface that we think about and interact with the network today. And then as soon as we had that nice model that handled a lot of this complexity around naming and retry and delivery and congestion control, we immediately went and started rebuilding the same logic again in our applications at a higher layer, right? That is what your retry loop is. Rate limiting is congestion control, right? Service discovery is naming. It's exactly the same principles that we have and that we have solved at L4 and below, re-pop up at L7. And the service mesh's goal is to like the networking abstractions that we deal with now, push that below the line that an application really needs to think about. And there's a bunch of different things that come into that, things like service discovery, things like automatic resiliency, automatic retries and circuit breaking, and these other things that make your system settle into a steady state that's healthier than it might otherwise be. And load balancing is a key piece here. And in particular, if we can enable client-side load balancing, we can do some really, really fancy things with point-to-point communication without having to go through intermediaries, without introducing more points of failure. And we'll cover kind of how a service mesh can enable this and how Istio does this. Then I have all these services now, and they're deployed everywhere. And one of the other problems that I face is that when I had a monolith, there were just a couple doors in. Right? There's a couple ports that this thing listens on, and then all the communication is internal, and then it spits out some answers. And so when I need to go secure this thing, it's relatively simple. I go lock down any port that's not the ones that I know it needs to serve on, and then I start to apply some IP rules around who can talk and who can't, right? And that's great in the static model, but when IPs change a lot and those things, this traditional model of network security becomes brittle, right? And so instead, really what we would like is fine-grained control over who can talk to whom, service-to-service communication. And additionally, within that, I would like to be able to say for specific requests, whether it's allowed or not, whether it routes to one instance or another. I want to be able to do fine-grained control over where and how traffic flows and what that traffic is and which is allowed. And then finally, I want to secure these things. So management and security kind of go hand in hand. And again, today the security primitive, the identity primitive that we use most often is IP port pair. And again, that does not translate well to a dynamic world. And so the idea is that we would like to issue identities to the workloads themselves. And before we issue that identity, I want to make sure that the environment in which that workload is executing is appropriate and that the workload itself is good. I don't want a developer building something on their laptop, deploying it into prod, and getting a production identity. It's the wrong binary. It's the right environment to get a production identity, but it's not a vetted workload that went through my build system. Conversely, I don't want a developer to run the production binary on their laptop and get a production identity because it's the right binary, but it's the wrong environment. Right? So we need if we can verify those two things, if we can authenticate the environment, then we can authorize the issuance of an identity, and then we can use that identity at runtime for policy and feel secure. And we'll talk about how we do this. And then finally, I want to talk, so a service mesh can touch each of these 4 areas and provide those features. But in my opinion, actually the coolest thing about the mesh is the way that it centralizes control. So before, all of the features that I just talked about can be implemented in something like a client library, for instance. And Twitter is famous for having done this with Finagle. And Linkerd, the original version of Linkerd, wrapped up that, right? The new versions of Linkerd do something different, but this is a tried and true thing. Google did this for years as well. We had client-side libraries that handled all of this. The problem is updates. I need to go to individual application teams and say, hey, rebuild, redeploy your binary to pick up my new version of the SDK. And now you need to start doing coordination because some teams update more slowly than others, and some versions may not be compatible across each other, and so it introduces a slew of problems. And critically, these systems traditionally did not allow any form of centralized control. I could not go and affect the retry policy of all callers to a service, even though they're all calling through the same SDK. So a service mesh centralizes this control, and what this does is empower a small group of people in an organization to be responsible for a huge amount of the operational expense. For example, a central metrics team that's responsible for metrics ingestion, collection, and presentation for the entire organization can operate that part of the mesh, can affect changes across their entire organization with just config pushes, independent of the other teams, and fully own that. And offer, for example, to other teams, here is a dashboard that you can go to see your services, right? And we can do the same for security, and the same for traffic management. We can move control out of the individual teams and into centralized groups. The other benefit is that because I have centralized control, I can also delegate that control, so I can give it back to individual teams for things that shouldn't be managed by a central team. For example, no central team is going to sit there and set retry policies and timeouts for every individual service, right? Individual service owners should set those for themselves, and you can delegate control to be able to do that. And then finally, when we need to affect change on the system, we need to be able to do it quickly, right? We need to be able to respond to a dynamic environment at the rate of change of the environment itself. And typically, pushing new binaries is too slow, right? So if my configuration is encoded in the binary, I need to go do a whole new rollout to affect a change. That typically is not fast enough when we actually have a production event. So we should be able to push configuration to affect change and not push binaries to affect change. And then you can start to do really, really nice things like treat your configuration in the same way that you treat binaries and do progressive rollouts and do this continuous deployment and those kinds of things. GitOps is the right. So Istio is a platform to monitor, secure, connect, and manage services. And let's talk about how it works. So classic story. 2 services are communicating. A wants to call B. From our perspective, it doesn't really matter a lot what the communication is or what protocols, but just to keep things simple, we can just say it's HTTP, right? But it really doesn't matter for us. So the first and the most critical piece of the mesh, and of Istio in particular, is deploying Envoy beside every application. And we call this a sidecar deployment. And this sidecar intercepts all of the network traffic in and out of this application. And this gives us the point to apply all of the policy and all of the resiliency features and the visibility features that we talked about, right? The network is the interface point with the outside world. If we can capture that, we can do a lot of really fancy stuff. So yeah.
How is the very basic question? How is the Envoy and the service how is Envoy doing that capture?
Perfect. So the question is, how does Envoy actually do that traffic capture? So we'll talk at length about some of the Envoy side of things, but the short answer is that we use, typically in installation, we use IP tables to do a redirect, but there's a variety of options there. So you can do things like BPF redirects to cut out some of the network hops and things like that. But in a traditional Istio install and in the installation we'll use in GKE, we're using an IP tables rewrite to a small set of rules to capture that traffic. And please raise your hand and ask questions throughout. This is for y'all, so yeah, I can sit up here and talk about this stuff all day, but the goal is that y'all understand things, so please interrupt and ask. I forgot to say that ahead of time. Alrighty, so we have a set of envoys, but envoys just sitting there don't do anything. We need to actually program them. We need to give them behavior. So that is the function of the Istio control plane, and it's composed of 4 pieces. The first is galley, and this is, if we think about our application as having a 3-tier architecture. We have the data plane, which is envoys at the bottom. We have a control plane, which is the things that control and affect the behavior of the data plane. And we have a management plane, which is what users interact with to affect change in the system. Galley is Istio's management plane. It is kind of the API server that is responsible for taking configuration from the configuration store. We're going to be deploying into Kubernetes, so Galley will go and talk to the Kubernetes API server for configuration. And it takes that, validates it, and pushes it to the other Istio components. This is also, if you've heard about Istio, one of the things that you've probably heard is that it's tightly coupled to Kubernetes. Galley is one of the ways in which we are trying to decouple the system from Kubernetes, because yesterday, before in 1.0 and in previous versions of Istio, all of the individual components will go talk to the Kube API server themselves for configuration, which makes it very hard to run them in a different environment where you don't have an API server. Now they go and talk to Galley, so the problem becomes run Galley with a config source rather than run the entire control plane with some custom config source. It's a much more tractable problem. So one of the key piece of the control plane from the perspective of envoys is pilot. Pilot is the piece that is responsible for taking configuration from Galley. This is stuff that you author that we'll be playing with a little bit later, things like virtual services and gateways, and then this Istio networking config. It combines that with a view of the world that it gets from a set of service registries. So again, in Kubernetes, we go talk to the Kubernetes API server to say, hey, what are the services that exist in the system? What are their endpoints? Pilot can also talk with things like console and Eureka as well. But at least for the example that we're doing in the Kube cluster, Kubernetes will be the service registry of reference. And so taking these 2 things, Pilot together builds a model of what the mesh should be, and then realizes that into configuration for envoys that it pushes to the envoys to control their runtime behavior. The next piece is Mixer. This is Istio's extensibility point. One way to think about it is an out-of-process filter extension for Envoy. So at runtime, Envoy gets a request in. The first thing we need to ask is, do I allow this request or not? Mixer is the service that it goes and asks, do I allow this request? Mixer takes that metadata about the request, goes and computes a verdict. This is where you can plug into Mixer your backends like authentication and authorization. This is where you can plug in things like rate limiting. This is where you can apply policy to kind of arbitrary L7 arbitrary attributes of the request, right? If we're talking HTTP traffic, we can do things like headers, user agents, that kind of metadata. If we're talking about TCP connections, then we can use the L4 attributes of the request, right? Port, source and destination IPs, source and destination ports, those kinds of things. The second function that Mixer serves, And these checks happen in the context of the request, right? So Envoy will hold up a request, ask Mixer, do I allow it or not, get a response back, and then allow the traffic or disallow the traffic. Yes, so do you have a caching problem there? Yes, there is caching there. We will talk about Mixer caching at length because there's a lot of complexity and subtlety there. But yes, you have to cache, otherwise the system's not efficient because you're just doubling the traffic in your system. You can't do that, so you have to mitigate the traffic to Mixer, and caching is the way in which we mitigate policy traffic. The second use case for Mixer is generating telemetry. So asynchronously and out of band, as Envoy is processing requests, it takes that data and pushes it to Mixer via its report interface. And from there, Mixer synthesizes attributes and pushes them to some metric backend. We'll look at Prometheus in here. I have skywalking written down, but we're actually going to be looking at Prometheus. I forgot to go change the slides, my bad. And so Mixer, the Prometheus adapter in Mixer is implemented in the binary. Mixer hosts a Prometheus web page that Prometheus goes and scrapes to get metrics about the mesh. And this is metrics about the applications, not about Mixer itself. And those are batched, and that's how we reduce traffic to Mixer in the report case, is every individual Envoy has a buffer that it keeps of report data that it flushes periodically to Mixer. And then the final piece of the control plane that we should talk about is Citadel. And this is the piece that's responsible for identity issuance and certificate rotation. So we will talk at length about how Istio issues identities that are used at runtime and how this whole certificate rotation infrastructure works. But the very short story is we mint X509 certificates. These are certificates that you would typically use for things like terminating a website with HTTPS, right? But we mint very ephemeral ones, live a couple of hours. They encode the identity of the service, and we do that authentication of the service, issue the identity, and then that identity gets used at runtime. And we'll talk at length about how that gets used, where it appears, and how we can use that in policy. Right, so together we call this the control plane. I did say Galley is more of a management plane component, but in general we refer to the Istio control plane. And the Envoys we'll refer to as the data plane. So now let's actually, given that background of the system, let's actually walk through that request. So A wants to call B. That was our initial setup. So let's see how that actually flows through the system. So first, Envoy captures that traffic with IP tables or similar. There, Envoy determines the destination of the traffic. And there's a bunch of different ways that we can do this, right? We can look at the IP address. So the application likely resolved the DNS name and gave an IP address. One of the ways we do that is do a reverse lookup on the IP address to determine the service name. We can do that in Kubernetes because we know all the endpoints for all the services. So if you picked an endpoint, I know which service it belongs to. And then Envoy has already in locally the full set of endpoints that A will communicate with. So when we see that A sent a request, we can look at it, we can identify that it came from B. And even if you're doing TLS in your application, for instance, we can look at the server name indicator to determine what service you're trying to talk to. So there's a variety of ways we can do this. And we'll make a load balancing decision. So we'll say, oh, I see that you're going to B. I will make a decision about which B to send it to. And we eventually pick one. And Envoy forwards the request. We don't necessarily know that there's an Envoy on the other side or not, right? The client is oblivious. But we forward that request. B happens to have another sidecar. That sidecar intercepts the request. And it asks Mixer to go do policy, right? It says, hey, I just got a request. Do I let it through or not? And Mixer will go do whatever verdict we have configured. And we'll talk about policy in Mixer later. But this is where we apply our service communication policy, for instance. But let's assume Mixer gave a thumbs up. Mixer said, yeah, let the request through. Then Envoy will forward that back into B. B will do whatever work it needs to do to assemble the answer. This can call other services, whatever it is. And eventually B prepares a response. It sends it back over the network. Again, Envoy intercepts that response, forwards it back to the client that requested it, and that client Envoy then forwards it back into the destination application. And then afterwards, both client and server envoys will report back to Mixer the telemetry, the metadata that they saw about this request. I will call out, this is something that has changed recently. So in Istio 1.1 now, by default, only one report comes in rather than both. So only the server side will report rather than getting server and client. But you can go and enable some options if you would like both sides. So in a nutshell, here is the full stack. Right? So Pilot for configuring envoys, Mixer for policy and telemetry, Citadel for identities, and Galley for config distribution. So hopefully now, I think we walked around and everybody should have GCP credentials. Is that a true statement? Does anybody not have GCP credentials? Raise your hand so that we can walk around and give the rest. No, they would. They're on a piece of paper that they're handing around, so it's not an email or anything. So if you didn't get a slip of paper, raise your hand and we'll come give you one.
Anyone still has extra ones that you can use?
All right.
People look out.
Yes. Okay, and then I know that there were some people that had issues with gcloud. I think y'all did. If anybody else is having issues with gcloud, we can actually go through and do this in the Google Cloud website as well, so you don't need that command line utility. So first off, I would recommend you open up an incognito window, and then you'll go to what? Console.cloud? Yeah. We'll go to the GCP website. This you would log in with those credentials that we gave you. I get to do my two-step verification. And so once you're holding, well, I'm waiting for, well, GCP will load eventually. So after, sorry, I want to be clear. I am diverging some from the written instructions. So the written instructions do this all in the command line. That's how I typically do it, but some people don't have the command line, so I'm also walking through here how we would do it in the UI. Yeah, is anybody having issues with the GCP credentials so far? Raise your hand, scream. We have people in the back that can walk around and help you. So once you're here, go ahead and create a new project. And after that project is created, you'll be able to go to the Kubernetes engine page, and that will turn on the API. Yeah. And then from there, you can go and actually create a cluster. We do, oh man, are we cutting off the bottom? Yes, yeah. So sorry, it's, and the provisioning will take a little bit of time as well for the cluster. That's why, ideally, I'd have you all do this ahead of time, but unfortunately, we couldn't quite. Okay, good. Oh man, that's annoying. Yeah, well, because I always use one. Okay, so those written instructions are missing a little bit. They are missing a call to set the instruction ID. Let me go.
Anyone else need help?
Liam, what is the incantation to set the project ID? Okay. Well, that's to create a new project, but it's gcloud config set project something.
Don't create a new project. Click the project drop-down so I can create it for you and build it set up.
Oh, beautiful. So sorry, don't make a new project. There should be a project in the GCP account that you log into. My bad. Yes. So sorry, so this is the markdown version of what is in GitHub. If you go to GitHub, but unfortunately I was missing a little command here. Alrighty. So how many people have actually started to create a cluster? Or are we still in the getting into the project and all? Okay. Just a second, let me.
It asks you for your credit card, you're doing it wrong.
Yeah. So the credentials that we're giving should have billing set up already. So this is in the modules install cluster. I had that up on the side and I actually clicked on it and looked at what they can do. What's next? Yes. So if you go, sorry, I exited this. So this cluster, README has the command to create the cluster. In particular, the only thing you need to set is use standard Envoy standard 2D cases. Oh, okay. So I don't have that. But that's fine. So that's the first thing you do. Change this to okay. Yeah, so any location is fine. As far as latency goes, US West is going to be the closest physically to here. But yeah, any location is fine. I would recommend that if you are just going to pick in the middle of the list, because if you look at the historical utilization of various GCP regions, they skew heavily towards the top of the list and the bottom of the list, like the literal list in the UI. So like Bs are like the B zones are almost always less populated and less full than A and C. So just take that tip. That's. Alrighty, are we progressing along? How many people have clusters that are creating or have been created? Yes, just so a normal cluster. And when you create the cluster's nodes, make sure that you do N1 standard 2 nodes. And so if you're doing it in the UI, there's a little drop down, and it says, it'll say 2 virtual CPUs. I will show you. Yes. Yeah, sorry. I have the CLIs, and that's what I anticipated. Yeah, let me. Gosh, this is. Oh, then you can just delete it, create a new one. No, it's not the default. So there's one thing that you need to change. Sorry, next time I will go update this to include pictures. That will make things.
Is that just to set expectations that are many people here who are doing this first time?
Yep. Okay, I will. Yes. No.
Also click this button here, and it'll give you a command line if you don't want to.
Yes. So if you use the Cloud Shell, you will be able to type and follow along there if you would like to, rather than your own terminal. And what the advantage here is that that's running in a VM in GCE. So if you have controls on your PC, like you can install things, you can install them there. OK, here's the cluster. So in particular, this is the setting that needs to be set. So everything is standard. The only non-standard bit is that when you actually go create it, pick nodes with 2 virtual CPUs rather than 1. All right, let me go. And then the yes, what? This is the setting here. So if you're going and creating a cluster, in the default pool, 2 CPUs. Alrighty, where are we on who has a cluster being created? Who does not and is stuck and needs help? How are y'all?
So there's a real so if you want to use this as a console and you'll need to clone into which is fine. So the DC already has access. So you just like and then there's one other there's no, it literally is. So does that console runs so literally this was a little larger. So you I hope that I can get away with CLI because it's like easier. It's just more fancy.
All right, and for people that are getting your clusters deployed, what you can go ahead and start doing is the next set of install instructions, right? So as your cluster is coming up, you can go ahead and do the Istio installation and the, let me update this, this is not here anymore. Go ahead and do the Istio installation. And after you do the Istio installation, you can go ahead and start installing the app. And again, just raise your hand as you get stuck, and we can help out.
I would assume they would do it automatically for you, right?
Alrighty, so I'm going to go ahead and in my cluster, I'm going to go ahead and deploy the Istio and the application. And again, these are just the other directories under that install directory. So if you're looking at GitHub, go to the root of the install. And this will provide a nice little overview of what to do.
Who doesn't have their cluster?
Yeah, does anybody still need help getting the cluster spun up, or do we all have a cluster now and we're going? In progress is fine, yeah. All right, and as you're installing Istio, you should see that it'll create a ton of things. So yeah, after cluster is done, move into the next directory in the install. So if you Yep. And if you're following in the slide deck, I actually have links out to each one. Alrighty, so are we starting to get Istio installed into our clusters? Yes, excellent. Yes.
It's not working for me in Safari, so I'm going to try to do it in Chrome.
Yes, that should be. And hey, as you're looking at the commands that you would copy and paste to execute, those are those assume that you're at the root of the Git directory, right? So if you did a Git clone and then you went into that directory, all of the commands assume that that's where you're at. And those are where I'm running them from as well. So if you see here, I'm in the training directory.
You want to say that people can Git clone in the cloud shell? Because
Yes,
people
and so,
the red rock.
yes. And so I do want to say if you're using the Cloud Shell, that's a great option. If you don't have gcloud installed or similar, you will need to git clone the repo in the Cloud Shell, and then you can follow along from there as well.
Someone's saying they're not seeing all this here.
Yes, it should be. Okay.
Yeah, One second, sorry. What do you mean?
Oh, that's fine. It's right. That's probably because that was the list originally was from 1.0, or now it's from 1.1. But thank you, I appreciate that. I'll do it.
I'll update that, yeah. So as ever with Kubernetes, if you're getting weird errors around like not being able to find things or stuff like that, just reapply the script again. So that's the beauty of declarative configuration versus imperative, is that with declarative, I can just push it until the server takes it. So if you're getting errors around not being able to find things, just run the script a second time and it should kick in.
Welcome to microservices.
Exactly. Yeah.
So if you're doing the kubectl install Istio and you're getting not recognized, just run it again.
So that's actually saying that the install didn't work. So go ahead and run the install one more time. The actual thing. So
yeah, wait for that to be then run the config second. Then you should have Kubernetes set. So just run the previous command and copy the settings based on
Alrighty, are we getting Istio installed? Show of hands if we're stuck, if we have issues. Sorry, I'm changing it every time just to trip people. Hey.
So just, I think that runs the job and then the spots, right?
yeah, that's the sort of stuff. Yeah, as long as it's successful.
Yeah, okay, so.
I think it's okay to have previous version of Istio installed and make sure everything's up to right. Yeah.
Alrighty, so I take it from the rising volume level that we have installed Istio successfully.
There is a link to
Let's.
current skywalking stuff already in the slides in there.
I remove that.
Okay.
Totally. All right, so if you're successfully installed Istio, go ahead, and the next step is we'll go ahead and install our demo app as well. And then we'll take a short break, to give everybody a breather, and then we'll come back and we'll start to look at some observability stuff. Oh, sorry. So skywalking, we're going to skip. I deleted that and I didn't get all of it, so I apologize. Yes, so it's in the install directory at install/app. Or if you're in the slide deck, I have links out to all of them. But so if we go here, there's it. Sorry. All right, anybody having problems? Everybody has Istio installed, is getting the application installed? I don't hear screams, so. Yes, so in that same, if you go to that link, or if you go up, it's all in that install directory. So here in install, we have Istio, and then if you go to the app.
Okay, it's another.
Yep, yeah. Yeah, we need to add next and back links to the markdowns to make it more easy, but I didn't have time, unfortunately. Alrighty, so my plan is we're going to rejoin back in about 3 minutes at 9:40 to roll into the next section.
Oh, good. All right, I'll be right back.
All right, now I assume from the lower level of volume that we're having problems installing the app, maybe? Hopefully not. So I'm planning on, yes, so I'm coming back in the next couple of minutes. So if you need to run real quick, then yeah. All right, so does anybody still not have the Istio and the app installed? All right, awesome. Need a hand or are you good? Oh, perfect. And hey, if you're not seeing the exact pods that I have in the list, it's because we updated it late last night. So there is so one or two of the pods should not be there. This is the correct set of running pods. Oh, except that you should actually follow the instructions so that you have sidecars, because I didn't follow the instructions, and here we are. All right, perfect. All right, so one of the things that I do want to talk about, because we don't have covered in the slides, is this kube inject command here. Right, so like I said originally, the vital thing for us to build this mesh is to install those sidecar proxies, right? And so fortunately, Kubernetes provides a pretty convenient way to do this. So pod is the deployment unit in Kubernetes. And fortunately, it allows us to put multiple containers together. And this has a couple different implications. So the biggest implication is that it means that those containers exist in the same security context. we actually abuse this fact in Istio to have the sidecar present a service identity on behalf of the application. And that's fine because they're in the same security context. And that's why we can do that. So how do we actually get that pod in there? How do we get those containers into the pod in Kubernetes? The Istio command line offers a kube inject function to do this. And what it will do is take your existing deployment descriptor, a pod spec, and it will inject in the 2 containers that Istio needs. And we can go look at this. Yeah, here we go. Okay, sorry. Let me find it here. And what we'll see, and let me just use the command because this will be easier. So what we see, we actually, in this one YAML file, we're deploying 2 deployments. One is a MongoDB deployment, which gets a sidecar as well, and we run this init container. The second is the actual user application itself, which also gets a sidecar and the init container. So earlier he asked, how does that traffic capture happen, right? So when I deploy Istio, I put those sidecars there, and they intercept all of the network traffic. That init container is where we apply the rules that do the traffic capture. And there's a couple different ways that we can do that, right? So I mentioned before, so we use an IP tables redirect by default. And you can use things like BPF as well. A second option that you have that's new in Istio 1.1 is an option that doesn't use an init container. So the problem with these init containers is that it requires privileged access to run. That can be fine from a security model because the init container goes away after it runs, right? So it runs once, it goes away, and the remaining containers that are running are not privileged. However, some environments you don't want any privileged containers running, period. And so instead, Istio now has a method of doing the IP table setup via a CNI plugin, right? So CNI plugins are the way that you can do custom networking things in Kubernetes. A lot of people are familiar with like Calico or Flannel as a CNI plugin. You can run a normal Calico network, for instance, and you can add in the Istio CNI plugin as well. And what that will do is let Calico set up your network as normal, and then we'll run an Istio, what is effectively this init container, that will do the IP tables rewrite. Then we'll actually start your container. And the advantage of that is that the privileged piece moves to the CNI bit, which is typically already privileged, and it moves out of the pod. So this is something that happens once on the node with a CNI plugin that's running once per node, as opposed to happening for every single pod. So in this one, we're still showing the kind of legacy way using the init containers, but there are other options that we have to do that installation. Alrighty, so does everybody have now the application deployed? The list of pods in GitHub is wrong, but this is the correct list that you should be seeing. The only version 2 that should be deployed is the user service right now. Everything else should be v1. Alrighty, excellent. So then we're going to go back to the slides and we'll talk some about observability. So we can actually start to visualize our deployment, see what we just deployed, and then start playing with it. All right, so let's dig into monitoring. In particular, in this section, we'll talk some about Mixer, what it is, what it does. We'll talk about how it generates telemetry. I forgot to update the slide. I'm sorry. We're going to talk about Prometheus and Grafana. We're not going to talk about skywalking. I lied. I'll go update these shortly. And then finally, we'll end up in a lab where we can actually look at some of the configuration that produces metrics. Alrighty. So I said before, Mixer really is the extension point in Istio. So if I want to go add behavior to the data plane, right? I want Envoy to implement some behavior. I want some policy, or I want it to generate metrics, for instance. The only tool that I have to go do that in Envoy is to go write C++, write a filter in Envoy, basically, and then bundle that into a binary that I deploy. right? And Envoy today does not do things like gracefully load dynamic filters and things like that. So I have to package it in with my binary, right? I can't do like a DLL or some similar dynamically loaded thing. And the bar for C++ is rather high, right? So I don't, most developers these days are not writing C++. It kind of sucks if the answer for, hey, I want my mesh to do more is go write C++. So Mixer was introduced. And there's a couple of different reasons for this. There's a great blog post as well on the Istio site that talks about, I think it's Mixer, the single point of failure myth. And that's a phenomenal read up on some of the background for why Mixer exists as an architectural component. But again, it exists as this extension point. So envoys at runtime call Mixer. Mixer is effectively a dispatch engine. It really is. It takes configuration that you give it, and we'll walk through this configuration at length. But the configuration looks like a function call, and that's because it is a function call. Because really, what you're configuring is, hey, Mixer, take this data, turn it into an object that looks like this, and then hand it off to Prometheus, or hand it off to Skywalking, or Sysdig, or Datadog, right? It's a function call. And so because of where it is in the mesh, and because it gets called by every single envoy, it's also the point that we do policy as well. And as a result, in the performance characteristics of those two things, the performance characteristics of applying policy at runtime versus generating telemetry are very different. So the same Mixer binary is actually deployed twice in two different versions, one for policy and one for telemetry. And that way we can scale them independently, and we can actually track the resource usage. So you can actually see how much am I spending on policy versus telemetry. If it's one binary, if it's one deployment, it's hard to tell the difference, right? And Mixer exposes three primitives. It exposes a check, quota, and report. Check, we talked about before, is policy. So Envoy says, check this request and sends metadata. It actually checks quota at the same time. So the check call does both a policy check and a quota check. And those quotas can be on things like on arbitrary dimensions of a request. So if I can pull out, for example, an API key, I can do rate limiting based on API keys, or I can do rate limiting based on IPs, or anything that any metadata that I can statically extract from the request. And then finally, telemetry, which we talked about. So if we look at like Mixer in the architecture, it looks a little funky because we have all this traffic going into this one component. It looks like the single point of failure. That blog post does an excellent description of why it's not. But really, more than anything, Mixer acts as a cache. So we have this problem. We want, if we're really trying to be security conscious, we should do things like authenticate and authorize user credentials at every single hop through our service mesh, or through our service chain, right? So traditionally, we do that at the front door. Something like an API gateway, a request comes into our system, it hits something like an API gateway or an external proxy, an edge proxy. That does some authentication of the user credentials, and it passes those in. And maybe our first tier of app is going to do auth-c, right? It's going to authorize the user can access the thing. But it's a pretty common pattern that after that we kind of drop the user credentials and requests flow, right? So my web front end does the user login, does auth in, auth z. You can do this action. It calls the backend, and the backend just calls the database and inserts some data. And the backend never checked that the user was authorized. The database never checked that the user was authorized. By the same token, and in general, we want policy to be applied every hop through our chain of services, right? This is how we get consistency. This is how we get the security, is that we know because I've set a policy, it applies everywhere, not just at the edge. You have a problem, though, if every single service is calling your authorization service. Because now you've just, one request comes in, it goes through 10 services. So you now have a 10x traffic multiplier to your authentication service. Because your one user request that you used to authenticate one time now has to go through 10 services that authenticate it once each. That's clearly not sustainable from many different dimensions, not least of which is just bandwidth. Like you just can't, You can't make all those network calls. And then your authentication service actually becomes your central point of failure. Because now, if it fails, every single service in the chain fails because it can't communicate and authenticate. So Mixer was created inside of Google. We had a similar component, and it exists to be a distributed cache, effectively, to isolate the leaf nodes, our data plane, from the policy engines by caching those results. And it turns out that we get pretty nice locality there. And that really is the key to why Mixer caching is effective. I have a set of services. They talk to one Mixer. Mixer is the cache. So an authentication request comes in or an authorization request comes in. Mixer goes to the backend, makes a decision, comes back, and caches that result. It then hands the verdict back to Envoy. Envoy caches that result as well and applies it. And then Envoy does its business. And then we hit the next service, and the service calls Mixer to authenticate the request, and we hit the cache in Mixer, and we can reply immediately. Envoy holds on to that. And now the second time the user calls through, Mixer doesn't get called at all. Yeah. So the question is, once Mixer makes its initial policy verdict, does Envoy have to keep going back to Mixer? And the answer is, we'll talk in just a second. Let me see where my. We'll talk in just a second about what's called the attribute protocol. So when Envoy and Mixer communicate, they use a set of well-known attributes that describe metadata about the request. Things like the source IP, the destination IP, the headers. And Mixer, when it makes a verdict, computes a cache key using those attributes. And Envoy caches on those same keys. And so the answer is no, Envoy does not have to go back to Mixer so long as the request hits the keys. And Mixer does do a job of computing the minimum set of keys that is required for a verdict to increase the cache hit rate. You're more likely to, yeah, right, we're not caching on superfluous things about the request that we don't use. We are caching only exactly the attributes of the request that were used for a policy decision with the goal of increasing the cache hit rate there. Does that answer the question?
Yeah,
Oh, sorry.
Load balancing scenario, right, where as a service, service S1 is talking to S2, and then S2 has multiple instances, and you want to load balance weight with S3.
Uh-huh.
So first the request comes to the Envoy of S1, maybe one of the pods there, and then first authentication happens, so you make sure that you're able to talk to S2.
Mm-hmm. That happens at S2, though, to be clear.
It happens at S2.
Yes, so you try to establish a connection. That connection, that is where we apply service-to-service policy.
Okay, so then it means that the pod and S1 is going to talk to in S2 has already been selected by Envoy.
Yes.
For the load balance.
Yes.
That decision, that policy decision has to go 60-40, add 60% of the traffic forward. That decision is done by Envoy and S1.
Yes.
And the traffic goes to maybe pod 1 and S1. And
Yes.
then Authorization.
Yes. And so this actually touches on maybe, or I think maybe you're touching on a fairly common misconception with client-side load balancing, which is, and maybe this is not, but when we do things like traffic splitting, this is a commutative operation. So when I look at the traffic coming into my service, it is the sum of all of the traffic of all of the clients coming into my service. And summation is commutative and distributive. Because of this, if I apply a rule around traffic at every single one of my clients, I know that it applies to the totality of the traffic as well, so long as the operation I'm applying is also commutative. Traffic splits are commutative. If I have 10 clients and I say send half your traffic here and half your traffic there, then in aggregate, half the traffic will go here and half the traffic will go there across all the clients. And this is a general truism of all of the load balancing that Istio does. All of the load balancing that we do is commutative. Therefore, we can apply it at the client and get the correct behavior in total as it comes into the service.
But then if you use 60-40,
Yes?
then it depends on which pod each client chooses as the first pod, which is 60% of the
So another important thing to remember is that we're doing request level load balancing, not connection level load balancing. So per request, I can decide which of the backends we're going to, not per connection that gets established and persisted. Does that answer at least part? Yeah.
But I guess if it's practicable to decide on where to send to, I guess that would be a session stickiness.
So you can do session stickiness, but the important thing here is that most of the time we're not doing L4 load balancing. We're doing L7 load balancing. So we're load balancing requests, individual HTTP requests, not individual HTTP connections, which will carry many requests. And so because we can do this per request rather than per connection, this means that things like 60-40 traffic splits, which you can't effectively do at a connection level, because one client that you connect may send way more requests than another one, we can do it at a request level. Does that answer your question? Yeah. So we can also do L4 load balancing, and that will have all the shortcomings that traditional L4 load balancing has, which is we establish a connection, and however much data goes through that pipe goes to the server that the connection goes to, right?
So what was the question also? Stickiness, you're saying it doesn't support stickiness?
No, so Envoy can do stickiness, yes. So there are a variety of load balancing algorithms that you can use to select destinations, and some of them include things like consistent hash-based endpoint selection, so that a client can't be sticky to a backend.
But that's not on the layer 4, that's on the, when you say stickiness, that's actually looking for layer 7.
We can do stickiness at both L4 and at L7. So the same general algorithm for that load balancing applies per request or per connection.
The other question is when we talk about the traffic split, is that the mixer gets involved or?
No. So yeah, that is the key detail. So I didn't say that directly, but that's what I tried to imply. So Mixer is not involved in traffic splitting decisions. That happens locally at Envoy, and by design, all of the ways that you can affect traffic shaping, which we'll cover in length in the traffic section, are independent of Mixer and can be applied locally at the client. So load balancing decisions are always local to the client, and that's an important feature of the system for reliability. Because if I have to go talk to a central system before I decide where traffic goes, then my availability is limited by the central system, right? But if, for example, we get a partition that separates an Envoy from its control plane, that would mean total failure. But instead, an Envoy that's partitioned from the control plane and can't get new configuration can continue to serve. And because of the resiliency features that exist in Envoy, we can even continue to serve pretty well. And as things like an endpoint gets moved and no longer hosts my service, Envoy will automatically move that out of rotation, even though the control plane's not telling it. And then when we eventually do restore our network and we can talk to the control plane again, Pilot will push all the correct data and Envoy will update and continue to serve now correctly.
I think the other question, maybe you can later on, is that sometimes the policy is not that clear until probably detail is some policy actually that goes by the Pilot when Pilot will push some policy.
Yeah. So the question is like which policies come from Pilot, which policies go from Mixer, how does that work? So we'll cover that a little bit more, but the short answer is that things that affect traffic go through Pilot, things that affect authentication, authorization policy on the request itself tend to go through Mixer, right? So if you need to talk to an external system to make the decision, it has to go through Mixer. And we'll cover this more as we go. Okay, so here's a diagram with a lot of lines that talks about all the traffic and configuration flows through Istio. This is not very helpful by itself, but here is the flow for policy. So as a user that wants to connect to our web front end, which logically talks to some backend, if we actually see the flow of the data, we'll go in through our ingress. This will make a call to Mixer to say, is this allowed at ingress? It'll go to the UI that gets routed from ingress, which is what the user requested. And again, we'll say, hey, do I allow this or not? And then finally, the UI will forward it to the backend, who again says, hey, is this allowed or not? And importantly, all of these can be encrypted with MTLS. We'll talk about the security side of it. But this is how we do service identities to authorize communication. Oh, I have an even better one. And if we look at just the telemetry side, it's identically the same. As the request flows through, first we hit ingress, then we hit UI, then we hit backend. Each of these in turn will send telemetry data back into Mixer. So how does it actually work? We'll go through this pretty fast. It's not. This is more important if you're trying to do things like extend Mixer to implement your own policy. As a user of Mixer, it's nice to have this reference to help put in context some of the configuration that we'll work with later, right? So Mixer exists as a couple different layers. So first, it has the APIs that Envoy interacts with. Our request comes into these APIs, and we need to determine, and that request has a set of attributes. Here's what attributes look like. So this is a selection of attributes. Things like the protocol, the destination and source IPs, the source port, basically this is all static information that we can extract from a request. This is the payload that Envoy forwards to Mixer. Comes in the front door. However, there's a lot of data there that we don't necessarily want Envoy to gather. For example, I don't want Envoy having every single Envoy in my mesh talking to the Kube API server to get information about what pod it is. I want Pilot to do that centrally and store that, or Mixer to do that centrally and store that and use that. And so this is where attribute derivation comes in. So Mixer in process inside of it has an integration with the Kubernetes API server. When a request comes in, we'll take some of this metadata. I don't think I have, this UID. So we'll take the source and destination UIDs, and we'll look up the pods in Kubernetes that they belong to, and get extra additional attributes about the Kubernetes deployment. That way we have environmental information in addition to request information that we can use to apply policy. For example, something that we may learn from Kubernetes that's not here is what is the physical location of the node. If I want to apply policy based on location, US can't talk to EU databases. I need to know if the database is in the EU or not. That depends on the particular pod that the request lands at, and that's something that I don't want the pod to know. I want Mixer to know.
Sorry, yeah, but so is that so the when you talk to the Kubernetes pod, is that on like watching authentication?
Yes, yep, totally. So how does that integration with the Kube API server work? It's all in Golang. It uses the Kube API client, which does all the fancy watches and all that stuff. Yes.
That's a policy that I configure to Istio.
So Istio does not support that policy today. But that is an example of a kind of policy that Istio can enforce if you pull the location information. We'll actually have a demo tomorrow of a policy system that does do location-based policy, for instance.
This is the policy that Istio supports.
Yeah.
Then it doesn't have to go to the Kubernetes server,
So no, for the particular example of things like determining location, Mixer will go directly to the Kube API server, because from Mixer's perspective, that is the source of truth for that data, right? In theory, yes, it could or should even go to Pilot, but the simple fact is Pilot doesn't have the APIs exposed to serve that information. Yeah, exactly. Yeah, so Pilot doesn't really expose APIs to consume its model. The only APIs that Pilot exposes are the APIs that Envoy consumes. That is an area that I think we'll probably see change over time because it is useful. There are some debug endpoints on Pilot that you can go to look at its state of the world, but that's not something that you can, in general, programmatically query.
Because if I'm a bunch of policies into Istio, then Pilot has to send everything to the API server and tell them that, hey, in future somebody's going to come and ask you.
No. So when you push a bunch of policies into Kubernetes, they'll go into the API server. Galley will pull them. And then it will either push them to Pilot, who will realize them as Envoy configuration, or it'll push them into Mixer, which will prepare its dynamic dispatch stuff to get ready for Envoy to call it and implement those policies.
It all goes to the Kubernetes API.
Exactly, yeah. So in fact, from Istio's point of view, the Kubernetes API server is the configuration database. It also happens to get used as the service discovery mechanism, but that's a coincidence. That's an artifact of how Kubernetes is built and not necessarily an artifact of Istio. Right, I could just as easily use Eureka or Console as my service discovery registry and still use the Kube API server as my storage. Anyway, so Mixer gets a request, we go look up the additional metadata that we may care about from it. And then we determine, okay, so now that I have all the data, what are the set of things that the user configured me to hand this data to? What are the set of adapters? Adapters are what we call plugins in Mixer. What are the set of adapters that need to execute for this request, given the attributes that are present? And we'll talk about how that happens. Once we determine the set of adapters that need to run, each of those adapters describes the data that it needs. And that data is in terms of those attributes. So we map those attributes into the values that the adapter consumes, and then we dispatch those values. And again, I will show you the configuration for what each of those things look like in just a second. So again, here is our attributes. I already talked some about this, but this is a well-known vocabulary that is established and fixed. You can go to istio.io. On the reference section, there is a link to the attribute vocabulary. It is well-defined, and it is fixed per version of Istio. Right, so this change, as Istio versions change, this attribute vocabulary will change. But in general, it's been pretty fixed. So adapters are what we call the things that plug in. They can be implemented in process as a Go extension, and there's a set of Golang interfaces that you would implement, and then you would compile your own mixer with your plugin in that binary as well, and you could deploy that. So that's fine, but that doesn't work well if I want one standard, like if I want to use the open source mixer, I can't go rebuild with all my own plugins, right? So Istio offers as well a gRPC interface for out-of-process adapters. So I can have my authentication system that exists today. I could put a small shim API in front of it that implements the Mixer API. And then I point Mixer to it. When a request comes in, Mixer, if it is a cache miss, will go forward it to my auth service. My little shim will do the transformation, make my decision, and then reply back, right? That's one method by which you can integrate with an existing service. And there's a slew that are around already, right? So if you're doing, for example, when we talk about precondition checks, when we talk about policy, I can do things like OPA policies, right? So if people are familiar with the Open Policy Agent, there's an adapter for Open Policy Agent. So any random policy that we want to do with OPA, we can have Mixer enforce at runtime with the caching for us.
Did you have to write that Open Policy Agent policy in their
Rego? Yes. Yep. So in particular, all this does is it literally bundles up the OPA runtime, and you give it a set of Rego scripts.
Insert the data and the policies directly as it's
Exactly. And so what actually happens is when we go to invoke the Rego engine, the instances, the data, the attribute data, gets fed in as parameters to the script that you write. And then you'll get a verdict out of that, and Mixer will hand that to Envoy to enforce.
Can OPA agent get some like state information?
Mm-hmm. Yeah, so it's normal OPA, so anything that like normal OPA could do, go read databases, go talk to other things, you can do with the plugin, right? It's like the full engine for OPA.
The other question is, you talk about like say some existing, like a service check and some wall services like external. When Mixer talks that it goes through the external, the service entry, or what's the best way for the Mixer to?
Totally. So yeah, when Mixer wants to go talk to an external service, what's the best way for it to do that? The short answer is Mixer does not get deployed behind an Envoy today, which means that when it goes to resolve an address, it's just going to use normal DNS or the IP address that you provide. But this is actually configuration that you put in when you write your adapter or when you point Mixer at a remote server. The address is part of what you provide.
So either we can go direct, or maybe we can go with the Kubernetes, some facilities there.
Exactly. So if you deploy your backend for policy in Kubernetes, you can give Mixer the Kubernetes service name, and it'll load balance across the pods, right? Just like normal Kubernetes services.
Is there any time when you add or remove an adapter?
Sure. Yes. All the time. So do we add and remove adapters? Yes. Typically, we do not remove them. They're typically only additive, but yes. So for example, we've added skywalking as an adapter.
Yeah, but there's no downtime when you do that.
Oh, yes. So importantly, these in particular are compiled into the Mixer binary. And so the only way that they're wired up to get called is via the configuration that we're about to talk about. So if you just remove that configuration, it won't get called, and the only penalty that you pay for it existing is in the binary, right? So the bits are there, but they're not getting called, so who cares?
Can you chain adapters?
Can you chain adapters? No. We have talked about that. It's hard in the general case. I made a push that adapters should be a DAG. You should be able to describe a DAG of policy that gets evaluated. Yeah, so you can have multiple adapters. You can have multiple instantiations of adapters. If you want one adapter that actually is 5, you have to implement the shim yourself, unfortunately. It was a decision to simplify Mixer that got made. Okay, so given that we have adapters, we have these attributes that are coming in, how do we fit the two together? The first thing that we have are handlers. A handler is an instantiation of an adapter. I have a Prometheus adapter. A Prometheus handler is a specific instantiation that has configuration. It knows where it's going to put the Prometheus metrics on the Mixer server. It knows what the shape of the metrics are. It knows everything that Prometheus needs to know to export metrics. Then we say, okay, so I have this thing that I can feed data. What is the data that I feed it? This is what we call an instance. So we take those attributes from the request, and Mixer turns them into an instance, which is a bit of structure. It's an object. It's a structured piece of data with well-known fields, with well-known types, where we put the values from the attributes in. And then we have to say, okay, so I have data. I have a thing that can take data. When do I give the data to the thing? And we call this a rule. So a rule says when a condition is true, and that condition is over attributes in the request, and again, I'll show you in a second, then give this handler these instances. So here is a handler. So Istio has built in a list checker. It supports inclusive and exclusive lists. And what it will do is go and hit a URL and at that URL, and that can be a file path. It expects a list of data. And at runtime, you'll give it an attribute that is the piece of data that it checks for in the list. And again, we'll show some. A more interesting one, for example, is the Prometheus handler. So what does Prometheus need to know to produce metrics? It needs to know the shape of the metrics that it'll be producing, right? Prometheus metrics have a fixed set of dimensions that have a specific type. So when I'm configuring how Prometheus is supposed to export metrics, I need to configure, and this is truncated, I need to configure what the shape is there. And we'll see the actual real Prometheus one in detail. So those are my instances. So I have Prometheus ready, primed up. It knows the shape of the metrics. Now, what is the data that I give it? This is an example of the request duration metric. Here, I say that it has a set of dimensions. This is, again, truncated. But I have at least 3 dimensions. And this is a small expression over the attribute. So our response code is one of the attributes that gets reported. And what this says is, take the response code, or if it's missing from the request for some reason, fill in a 200 by default. In these other ones, we see that if destination service isn't present, it'll just fail, actually, because there's no alternative. And if the version label doesn't exist, we'll get an empty string. And these are values that actually get handed to our adapter at runtime. Similarly, if we're looking at our list checker, I need the value that I'm going to be checking against the list. And in this example, all we do is pull off the version. So the list checker would expect a list of valid versions as its configuration, and we check that the application version is there. And then finally, when do we fit the two together? So this one says, when we're talking to a specific service, service 1, give Prometheus the request count and request duration metrics. Or really what this is saying is, when a call comes into service 1, generate these metrics in Prometheus. This one is a quota configuration. It says, hey, there's no condition. So for every request, so if there's no condition, it defaults true. For every request, call our quota implementation, our rate limiting implementation, and pass it the request count quota object so that it can make a quota decision. Finally, there is a bit of configuration for how Envoy actually talks to Mixer. So this is an extract of the configuration that Pilot sends to Envoy. And here we can see that we actually statically encode the values that we know about, right? So Pilot knows the pod that Envoy is sidecar for. That pod is going to be the destination for requests that come in. So we can go ahead and wire up the destination attributes statically ahead of time. Similarly, on outbound paths, I know what service I am, so I know the source of the request that's going. So on outbound paths, we can wire up the source attributes. And this is how we get static attributes into the system. So what I actually want us to go do, so sorry, I need to change this a little bit. Let's actually go and look at some of this data. So I actually want to see how Prometheus is working. What does it actually do? So if we go over to our lab, we can go over to the observability section and start to see our app for the first time. So y'all can go ahead and do that yourselves, and I'll start to do this in the background for y'all as well. And by the way, I didn't ask, but this is legible for everyone. Can people see? Does the terminal need to be bigger? Sorry, the screen also cuts off the bottom, so it's okay. So if we go look at the application that we deployed, we didn't really talk about before, but it's just a small sample banking application. When we come in, we can't just log in. We actually need to go create an account, so we can hit join now. And do actually make note of your password, because the UI won't let you in if you don't type your password correctly. And again, this is local in your cluster that you've deployed. So if you go there, and again, I'm sorry, so just if I went too fast, I moved over to the observability section of the training. I have this in a little bit the wrong order, so I apologize. But we want to go to the observability lab if you're slide 70 if you're following in the slide deck. All right, so we have our banking application deployed. Really what I'm doing here is just generating some traffic so that we have some things to look at in the UI, right? So if there's no traffic into our demo application, there's no metrics to see. So really all that we're doing here, just go in, I'll transfer some money between accounts. Clearly there's no enforcement because I can go wildly into debt. But the point is we're just generating some traffic so that we can see this in the metrics. That we'll go look at in just a second.
How do you send it to
Sorry. So when you actually go to the UI, you will need to hit the Join Now button initially and create an account. This is all local to your cluster. It's stored in a Mongo that's there, but that password is enforced. So make sure that it's a real password, because you will type that in when you go to login. So if I go here, I can type in Zach, and my password is Zach, and I can log in. Again, so just click around a bit. The goal here is to generate a little bit of traffic. And just to make this a little bit more interesting, what I will actually do is go ahead and just start. I'll just start a little loop in the background that's generating some traffic. So here. So here I'm just grabbing that IP address, and then I'll say watch that. Cool. Okay, so all I'm doing is setting up a little loop in the background that's generating some load. All right, so after we've gone and kind of clicked around a little bit, we have some data, we have metrics. Let's go actually look at things. So in our Istio installation that we did, we actually deployed quite a few components. We didn't really get a chance to look at this, but if we look at the services that are deployed in the Istio system namespace. This is where all of the Istio components live in Istio system. We see that there's a whole slew of different services that are deployed, but in particular, because we're going to go look at metrics, we care about Grafana way at the top there. So Grafana is a dashboard UI for viewing Prometheus data, or for viewing a variety of data. Prometheus is one of them. We'll also, in a second, look at Jaeger traces, and we'll look at Kiali, which is a UI that is an open source UI for Istio that that we can use to visualize our graph, our deployment. So first, let's go see metrics. So one of the key advantages to Istio is that I can generate metrics, application level metrics for every single application in my deployment. And what's even better is they are consistent. So that rule, that Prometheus rule that we have, applies for every single service. So every single service will be producing the same metrics with the same dimensions, and those dimensions will have the same semantic meaning because they're coming from the same data every time. Having apples-to-apples metrics is critical because it means that I can build consistent monitoring dashboards. I can build consistent alerting pipelines. I can build consistency as a key enabler of automation. So if you go through the training, the first thing that we'll do, our Grafana service is not actually exposed out of the cluster, right? So if we look here, we can see that there is no external IP address to access it. So what we'll do is use the kubectl command to forward the UI locally so that we can actually go look at it on our machines. And so I went ahead and started that in the background. Oh, let me open that in a new window. Oh, man. Bad cache loads. Yeah, so I'm doing a port forward here from my cluster. So what I'm saying, so with this command, oh sorry, I started that in the background. Let me yes, exactly. So what I killed the port forward. Here's this command says, hey Kubernetes, get a pod name. So if we just look at this one part of the command, this just pulls out the Grafana pod name. If instead I just said kubectl get pods in the Istio system namespace, then I could also just copy and paste it out there, right? So all we're doing is a little shortcut to grab the pod name, and then we say, hey, port forward that pod in the Istio system namespace from the remote port 3000 to my local port 3000. And then I'll just run that in the background so that I can keep my terminal. And we knew that it was port 3000 because I look at the Kubernetes service definition and see that it exposes exactly one port. So that must be the port that I care about.
If you're on Cloud Shell and you want to run like port 3000, there's a button that says like open port or whatever, and you just change it to 3000 and it'll open up.
In your local browser, yeah.
In the browser. There's a button that looks, I don't know what it looks like, a diamond.
Yeah, so for those of you in Cloud Shell, there's a little diamond that you can use to port forward from your from the GCE VM into your local machine. And that's fun there because you actually have two SSH port forwards there. You're doing one port forward from your cluster into your VM and then from your VM into your machine. All right, and eventually, after you've done the port forward, what we should see is you should be able to get to Grafana. And Istio, by default, ships a whole set of dashboards out of the box that render the default metrics for you. We have metrics about the individual Istio components themselves. And from our perspective, we really care about the services. And in particular, I know that I'm sending traffic to the default service. And so here I can actually go and see, I can see how many requests clients are sending, how many requests the server is actually receiving. If those numbers are different, you're in trouble. The error rates, the latencies, I can go look at our response code. So far, we're only returning 200s. I can see most of the time we're even returning 200s pretty fast, 5 milliseconds. That's like pretty sweet. We can render HTML really fast. Great. And so again, the critical thing here is that these metrics by themselves are cool, but the really powerful piece is that this dashboard was built once, works with every single service in our, let me find one that I'm actually sending traffic to, sorry. It works for every single service in our system. Let me find, there we go. Let me make a transaction and then we can see some transaction traffic. We should see one request come through. But the point is here that we can build these uniform dashboards. We can build uniform pipelines that process the data that is now coming out of our system. And it's not just metrics, I want to be clear, right? So we can also have uniform access logs. I want every single server to produce exactly Apache access logs. Or I want every single server in my deployment to produce a structured log as a JSON blob. And I want it to have exactly the same fields everywhere. These are the kinds of things that we can do with Istio. Yeah, and for those of you in Cloud Shell that are doing the forwarding, you're going to have to not do it in the background because you're only going to be able to forward one thing at a time. So you'll have to kill the Grafana port forward to look at the Kiali one. So sorry about that. Next time I will include better instructions for people doing the Cloud Shell stuff. Alrighty. The second cool thing that I want to show off here is Kiali. This is another open source project that was started by Red Hat. Yes, I want to finish this first, and then we'll take a couple breaks, and then we'll take a few minutes. So Kiali has a bunch of interesting information, but perhaps most interesting to us is it provides a view. It provides graphs of our deployment. Sorry, I know this is not particularly visible for y'all. Sorry, zooming in is hard. So what's great is we can actually visualize our deployment and see traffic flowing through it in real time. And there's a variety of options here, but this actually tells us what is our deploy topology. Here I see, the UI server. So like one of the things that I can look at this and immediately learn. This UI server is not actually hitting any backends. This UI server is rendering a UI that I'm seeing at ingress, but all of my calls go from ingress to user and ingress to transaction to other services. So clearly my UI backend is not the one talking to my service backends. That happens at ingress. That's one thing that we can just immediately look at and learn, right? Another thing that we can immediately see is accounts is not accessible from ingress, right? It's hidden in my graph. There's a ton of great stuff here, and Kiali also supports things like showing whether the channel is encrypted or not, right? So I can use Istio to enable mutual TLS. Kiali will color. So right now we have mutual TLS off everywhere, but we can actually see that Kiali will color the edges between my graphs based on whether it's secure or not. And for example, as we use Istio to incrementally enable mutual TLS across our deployment, we can track that.
Is it picking up the data from
Yes. Yes, exactly. It's actually picking up, so Kiali is actually backed by the Prometheus data. So Mixer exports Prometheus metrics, Prometheus goes and queries those. Grafana is built off of that Prometheus data, and Kiali is also built off that Prometheus data. So it's coming from Mixer, but it's one channel of indirection there.
These are just the way how the communication is set across the services, right?
This is the actual observed communication across the services. So this is observed based on the real request data. No, this was, I'm sorry. Yes. Yeah, so sorry, I did not make that clear. This graph is dynamically generated at runtime from the metrics. And so this is a real representation of how traffic flows through our system, not some pre-made representation that we use to affect policy. Now, once we have an observed graph, we can use it to start to affect policy. I can start to do things like lock down my traffic based on the things that I know communicate. But yeah, this is generated dynamically from runtime data.
But a stupid question, is there a way to graph what is being configured?
Totally. So that does not exist today. So in a later section, we will talk about the Istio RBAC, and which describes how services can communicate. It turns out that if you build an RBAC policy for this, it looks a lot like the DAG, looks a lot like the graph. And so yes, UIs and tools will exist to, and some have already been built. To my knowledge, none have been built in open source that will take a graph like this and generate a set of policies that enforce it. Right? So like this is something like Tetrate does. For example, is we do service auth-in, auth-z. You can look at the graph and we can lock that as your allowed policies. Because and the reason for this is most of the time nobody knows that getting this information, you typically would have to go talk to like 15 different developers, right? To be able to draw this. Exactly. And so this is exactly. Yeah, and then the final thing I want to show here is tracing, which is another just incredibly powerful tool for understanding our system. All right, so I actually, in this case, I want to look at traces from the ingress because I can see very clearly in my graph that the ingress is where all the action is. So if I want to see a request, let's start with ingress and we'll go from there. Right, and this is how these things, so hopefully you can also start to see how correlation might be an incredibly powerful tool if you can take those graphs and correlate them with all the other data. For example, these traces. So here I can see a whole lot of calls to the UI. That's because I have a little loop running in the background here that's only calling the UI and not doing anything else. So let me make one trace real quick that is a little bit more interesting. So if I go here, I go to my checking account, we'll do that, and I'll do a transfer, and I will submit that. And if we go look, hopefully we actually sampled that trace. We should be sampling every trace. Okay. So here's one thing I want to show real quick. First off, we did actually, so here is a very small trace. This one went just from ingress to the UI. I can see that it took 18 milliseconds total, and we can actually see the tree of calls, right? So I can see, hey, the UI actually, clearly some of this had to be network latency, because I know for a fact that this check, this mixer check occurs when the request hits my sidecar. I know that this trace started when my user request hit my ingress proxy. So I know that this latency is the time from ingress into my UI. I know that this latency is my, or actually, I'm sorry. Oh, this is an outbound call. So this actually went to hit a database that we don't have tracing on. So what I see here is we actually made a check call at our database, which is not present in our graph. Let me find one that has more. But the key thing that I want to highlight here is that most of these traces do not have a mixer in them, even though mixer is logically being called every time. That's because we're getting cache hits. So that mixer request that we saw was a cache miss. But I'm sending uniform traffic. I had a curl loop from my one IP address that was just curling the UI. I should be getting cache hits almost 100% of the time, right? The only time I should not get a cache hit is when I expire out the entry and then need to go fetch a new one. And here we can see that our traces are largely confirming that. I'm not calling mixer, even though I know that it's configured and is being called. Oh, thank you. Yes, thank you. I had written down which one to check, and so here we go. So our that's the other thing that we can see from our graph is that our transaction service is responsible for doing some of this coordination here. So that's another fruitful one to look at for traces. And so if we go look at it, we can see that this is pretty interesting here. So this is what I might expect. Ingress is calling transaction. which hits the service. We do our checks. Then we actually hit the service and call out to the account service. This is this edge in our graph. And I can see that that also hit a mixer. So clearly, we didn't hit any cache things through this request, right? Not yet. So this is some of the correlation that I was talking about that does not yet exist in OSS. I would argue you can correlate which users per path. And tracing is exactly one of the ways that you can do that across services. And then within the context of a single service, you can do things like mint a unique request ID and include that in logs and in metrics. And so that's what Istio does. So when a request arrives at a sidecar, it actually gets a unique request ID that is minted. Envoy prints that in logs. That gets passed into your application that you could attach to logs if you wanted. Yes. So the unique request ID is generated per service by Envoy once locally. But the way that distributed tracing works is by propagating metadata between the services. So in Jaeger, there's a set of 5 headers that get attached to the HTTP requests that flow through. And yes, your application does need to propagate those headers out, right? So Envoy will establish those headers in. And here we know that it does because I see the ingress trace. So I know that my ingress proxy established a trace span. It forwarded that into the transaction service. The transaction service forwarded into itself. It called itself here. It called itself again, and then it called the transaction log. And again, throughout all of these calls that occurred, it was forwarding these this trace metadata, so that as requests hit each of the services, they all independently report back, and they say, hey, by the way, I had this trace. And then in the back end, Jaeger joins that data together as it streams in to present a tree.
One thing I would say that is important to note is that one of the big advantages of this is that if your app is not participating in trade, the proxy will fill in a bar that says,
Unknown
this
here.
call went into this service that doesn't participate in a trade, that will be long. So you won't get a gap in your trace, you will get a full trade.
Yeah.
And then the proxy will say, I called this thing and it took about this long, I don't know what the hell it did, but it took this long.
Exactly.
So you won't end up with a trace with big gaps in it.
Exactly. And what that does is it also lets you start to zero in on the things that don't have tracing, right? Okay, so I want to so at this point, the final thing that I want to do before we take a break, because I know the session has gone long, is I want to show some of that Prometheus configuration. So I alluded to it on the slides, some of this, how we wire up Prometheus. Here we can actually look and see the constituent pieces. And there's a lot of config here because there's a lot of metrics. So if we go and ask Kubernetes, hey, what is the thing? We say, hey, this adapter is compiled in, it's Prometheus, and here's the request count. And request count has these labels. Total requests takes a bucket, and here are the labels, and here are the buckets. Our duration is a distribution with exponential buckets, right? So these describe the shape of the Prometheus data. If we look, we can see that we have a bunch of different metrics. These correspond to the Prometheus configuration there corresponds to these metrics. And if we go look at one in particular, for example, the request count metric, we can see here's a whole bunch of dimensions on that metric. That request count metric with those dimensions are what backs this client request. Let me find one with some data. Sorry, let me open up my window there. So like these requesting client metrics are built using those dimensions. And I can actually use them to slice up the data. So I can, for example, and they changed some of the UIs on me. You can actually do things like filter based on caller and source and destination. So I can look for this particular set of services, what's the health. I can look at for any service, what's the health, and those kinds of things. And then finally, there are a set of rules that where we feed Prometheus that data, right? Exactly like I talked about. Here we can see that there's actually 4 that Prometheus does. And in particular, Prometheus splits out HTTP and TCP metrics because they have different dimensions. And if we go, we can look at and this says, hey, sorry. This says, hey, when the protocol is HTTP or gRPC, and it's not Kubernetes probing, give the Prometheus handler these metrics. And that is how we get that data that flows through that we can see in Grafana. And so with that, let's take a little break. Let's try and be back by 10:55 because we're running behind, so we need to pick up the pace. And then we'll go. And I think that there are snacks in the back as well, it looks like. Yes, sorry. I will throw that up here. Somebody remember that we are on 78. So here for people that came in later, here's the link to the training repo. Here's the link to the slide deck.
Thank you. Yeah, sorry.
So I spend a lot of time. I need.
I think you don't have to pay the price.
Yeah.
We look at it.
Thank you. Alrighty, folks, let's start filtering back. We want to start again at 11, so another 2 or 3 minutes.
Yes. Yeah. So all it does is the exact same thing as the innate container, which is by default it runs an IP table script that redirects all traffic coming into the network namespace into Envoy. And so Envoy listens to port 15,000. And so those IP tables says everything coming in and everything going out, send it to port 15,000 on Envoy. And then Envoy makes a decision and send it to So I want to be very clear about the distinction between the network that a CNI sets up and the CNI plugin itself.
They were asking what it is.
What kind of check? So today it does not. Is the short answer. And then the other thing is that there are other mechanisms that can be used other than IP tables. For example, there's something else that shipped VPF version. Exactly. And so you can actually use the CNI you can actually use the CNI plugin to configure the VPF traffic capture instead, right? So those are, one is, it's really, the CNI part is a delivery mechanism, and then you have a traffic capture mechanism. And so you can use an init container or CNI to deliver any of the traffic capture instances. And so that's actually what Citadel does. So it uses Unix domain sockets to bypass the network from the application into Envoy. So normally you go through that application. I'll talk more in detail. You go through the network stack 3 times, right? So you go out into Envoy. So out from the app into Envoy, and you go out to the network. But you can do BPF to go UDS. Yeah. So check out the CNI. So CNI has all that stuff, and it's just an install options. Totally, exactly. So all those are available. Yeah, so there is the site. You have repo still public as well. There will be the video afterwards, and then you can email as well. Great.
Alrighty, everybody, let's start bringing it back in. Let's go ahead and start sitting back down. Alrighty, thanks everybody. We're coming back, and so I heard feedback that it was too slow and we weren't covering enough content, so we're gonna have to step up the pace. So I do apologize. This is a huge amount of content that I am throwing at y'all. So I know. That's why there's video to go back to later, and the slides and the GitHub stuff will all be there for you to go to. And you can always email afterwards. But I was only kind of half joking. We actually are running short on time and we're not covering enough material, so I want to get into the meaty stuff. So I will be skipping over some things to kind of abbreviate the content. So we won't talk about how, so there's some auxiliary slides here that we won't talk through about how Mixer actually does all of this stuff. We're not doing skywalking things. So let's, from this point on, let's dive into traffic management. And this is hopefully some of the more interesting things for people. Hopefully all of it's been interesting. We'll see. And so here we want to talk about the data plane, Envoy. We want to talk about Pilot, the control plane, the thing that's programming it. And we'll talk about how traffic actually flows and how we can affect traffic flows through the system. So we say, that traffic policy is configured by Pilot and implemented by Envoy, right? Then this is our data plane versus control plane distinction. And the reason that, so there's a bunch of different web proxies that are around, right? And when Istio was being created back in late 2016, we were looking around to try and decide what proxy would be used as the sidecar. And there were a bunch that were in the running, right? Nginx was kind of the obvious choice at the time. Envoy was new and little known. It had actually just been open sourced a couple months earlier and was not really popular yet in the way that it is now. But Envoy has a lot of things that make it incredibly compelling for the sidecar use case. And I want to point out that Envoy was not originally intended for the sidecar use case. It was actually deployed at Lyft as their software edge proxy, right? And that was the origins of Envoy. And it inside of Lyft, it migrated into the sidecar use case, the sidecar pattern, and Istio picked it up to use it in the same way. There's a couple of things that make Envoy incredibly attractive for this use case. One, it's got a pretty small footprint. Right, so the Envoy binary itself is pretty small. It's a couple megabytes. Envoy's resource utilization itself is pretty good. It doesn't use as much RAM as, for example, another competing sidecar at the time was Linkerd v1, which was at the time JVM based. And so if you look at the resource utilization of a C++ proxy versus a JVM based proxy, it's worlds different, multiple orders of magnitude, right? So Linkerd v2 has addressed these, and they've moved to a Rust-based proxy, so it's a lot smaller now, right? They're comparable. But if you look at that, that's one key benefit. Hey, I get to reclaim hundreds of megabytes of RAM per pod that I'm scheduling, and I have lots of pods. And arguably more important than that even is the fact that from its very beginning, Envoy is API driven. So all of the behavior that I can affect in Envoy can be controlled at runtime by APIs. So I can dynamically push configuration to an Envoy that changes its runtime state without having to restart Envoy and without having to drop connections. This is how the mesh actually works, right? So when I go, and in a second we'll mess around with some routing rules, and we'll push some routing rules and see them take effect. Those are affected without restarting proxies and without having to drop existing connections by Pilot pushing configuration dynamically to Envoy. And this really is the most novel piece of Envoy that was really the heart of why that was what we picked for the sidecar.
Can you comment about Cilium's intersection?
Yeah. So
with Envoy and
totally.
can that be used here?
Yes, yeah. So Cilium is doing. So the question was, what is Cilium doing here? What's some of the intersection there? Cilium is doing some really cool stuff with BPF. Right, so for those who don't know, the Linux kernel has a small virtual machine inside of it that is BPF. It's called the Berkeley Packet Filtering. And it's how tools like TCP dump work. So if you've ever used TCP dump, that actually is a BPF program. So Cilium is doing some really, really cool stuff in the kernel, and there's hooks for this virtual machine throughout the kernel, and it lets you do interesting behaviors. One of them that Cilium has implemented is bypassing the network stack from sidecar to application, right? So with a naive IP tables capture, when an application sends data, it goes through the kernel networking stack, and then it hits the IP tables where it's rerouted back to Envoy. Envoy does its processing in user space and then goes back through the network stack again to hit the actual network, right? So one of the advantages of using BPF is that we can actually cut out that application to Envoy network trip. And instead, we can do Unix domain sockets and just copy the data. So we can actually have we can share those buffers between the two and become much more efficient and not have to go through the stack. So there's some fast paths to get picked. So there's a variety of things like that that BPF can be used for, and Cilium in particular is shipping that. We did not use Cilium's version today. Today in the install, we just use the default, which is IP tables based. But you can go and use the BPF base.
Well, with that, the Kubernetes network policies, will that still activable if we do the
Yes. So because all of the like Cilium stuff, for example, the BPF bypass is happening local in the node networking namespace, like in the pods network namespace. It should work fine with your CNI, your existing CNI plugin that's building your Kubernetes network.
But let's say if you radical, the network policy actually by the IP table, right? But you can bypass that.
Is it? I don't. Calico actually uses BPF. Sorry, uses BGP to implement its network policy.
So
what you're asking is, can you use network policy between? Does this bypass the network policy?
Yes. Yeah.
But you can't do network policy between pod and a sidecar because you can't do network policy in the pod context.
Okay.
Yes, yeah. So we don't actually leave the pod local network to do this, and so
Just between the sidecar and the pod.
and the real network, yeah,
Let's say between like one service to the other service, that still goes through
the real network, yes,
Yeah, but
It goes to the kernel.
yes, yes,
Okay.
yeah. So that because it has to hit the real networking stack, right? So we can cheat and skip the real networking stack once between the app and Envoy because I know they're both local. But when I actually go out to another pod, I don't know if it's local or not. And so I have to hit the real networking stack, and that's where, yeah. Cool.
So,
Thank you.
but even IP tables and EB can coexist in this case when it comes to layer 4 unmatched
Yes.
IP tables to honor any of Kubernetes network policies or Calico network policies.
Yes, so yeah, those should work together fine. The critical detail is that BPF is between the application and Envoy where you didn't have network policy anyway because you're on the loopback. And so it's only when you leave that you're going to start to apply your Calico policy.
So at the same time, you could have your Calico CLI BPF also. Because these two are part of
It is not there. Calico doesn't.
No, I'm saying, ACLI, just quickly Calico.
Yeah, Calico
Yeah.
doesn't support.
Yeah, not today. Yeah, good questions. And then the final piece that I want to talk about with respect to these APIs is the Envoy's new APIs are push-based. They used to be polling-based, and this was a large source of pain for scalability in Pilot because as the number of workloads increased, the amount of traffic to Pilot increased because they would poll periodically. But today we have a push-based system where using gRPC, Envoy establishes a long-lived connection to Pilot, and Pilot will push data as it computes changes. And so the end result being you can have much more concurrency in the system. You can have much more envoys connected to a single pilot, and a single pilot can handle many more connections.
So we are doing the sticky connections.
Yes.
If you change the policies to Pilot,
Yes.
would you reevaluate the existing connections?
It depends on the specific change that you're making in Pilot, whether or not you would need to reestablish connections. And the important thing with connections is your question is really more about sessions. So connection stickiness is actually a property of the load balancing algorithm, but you're talking about keeping a connection open. And the answer is it depends on the specific type of change that you're making in Envoy configuration, whether or not it has to close the listeners and as a result close connections that are open or keep them open. So one example of a case where we close connections intentionally, and this is a design decision, is that when we rotate the service identity credential. So we use a certificate that represents the service's identity. We intentionally, when that gets rotated, we close the current connections and open up new ones so that they're established using the new certificate. That's not required because an existing open connection can happily use an expired certificate. That doesn't matter. But as a security posture decision, Istio by default will sever connections on cert reload, for instance.
And you can customize how long it will wait before it establishes a connection as well.
Yeah, and so those are configurable options. Alrighty, so real quick, Envoy has Envoy's core configuration that we deal with at runtime has 4 primitives. It has listeners. Listeners have routes. Routes send traffic to clusters, which have endpoints. And so here's a picture. So we talk about those APIs that Envoy has are called the discovery service APIs. So each of these nouns, listeners, routes, clusters, and endpoints, have their own discovery service. We call these the route discovery service, the cluster discovery service, right? Collectively, we call these APIs the XDS APIs, so the X discovery service. And that's what I'll refer to them as in this talk. So if I say XDS, I mean the collective set of configuration APIs for Envoy. So we load listeners, which have routes. A listener is going to bind to a specific port. So a listener is going to say, we'll have one listener for port 80, for example. We'll have one listener for port 15,000. And listeners come in two flavors. You can have a physical listener, and a physical listener actually binds to the port. Or you can have a virtual listener which doesn't bind to the port. Virtual listeners are used for routing, and we'll talk a little bit about that. Inside of those listeners, and those listeners are where we actually wire up Envoy's behavior. So Envoy is a filter chaining proxy. This is how most proxies are built. So I have a chain of filters inside of Envoy that I want a request to flow through to get behavior. For example, I have a TCP filter, and the TCP filter feeds into the HTTP filter, because I need to process the TCP bits first, and once I've unwrapped the TCP payload, I can unwrap an HTTP payload, right? So I need those in order. Listeners describe the filters for each port. So if I'm listening to HTTP traffic on port 80, there will be a different set of filters in that listener compared to a TCP service that's listening on port 53, or a UDP service on port 53, right, if I'm proxying DNS. Inside of those listeners and specific to the protocol are going to be routes. And this is really the heart of how we do traffic shifting. This is where we get into things like the per request load balancing in Envoy's configuration. So a route might say, so inside of a listener, I might say if you're going to foo.com, I have 5 routes, and you'll hit one of those routes and be directed to a service. And so a service is a cluster. This is going to be maybe the most confusing bit of terminology here. So Kubernetes, we have clusters. Totally different than these. A Envoy cluster is effectively a Kubernetes service. It is a group of endpoints that are logically the same. And this has a bunch of different information about how I talk to those endpoints, right? So I have a cluster that is, foo.com, and I have configuration around circuit breaking. When do I know to stop calling endpoints? Load balancing, what is the algorithm that I use to select endpoints of this service? How do I communicate with it? What's the TLS settings? Is it mutual TLS? Is it simple TLS? Do I present a certificate or not? Which certificate do I present? That's all inside the cluster. And then finally, you have endpoints. And these are the actual network identities I'm going to route to. These are IP addresses. These are IPs and ports, right? So in Kubernetes, these are the pods. And then finally, secret discovery, how we load in certs. That's actually done kind of via side channel API called the Secret Discovery Service API. And certificates can appear in listeners. These would be certificates that I use to terminate traffic, right? So incoming traffic in, I'm going to catch and I'm going to terminate. I need certificates to terminate TLS. And then on the outbound side, if I'm going to do mutual TLS out to a service, I need certificates to establish that connection. And the secret discovery service is the way by which we can actually provision the secret data, the actual bytes of the certificates. Yeah, so we'll talk about Citadel and how certificates get loaded at length at the end. Yeah, so in Envoy, an upstream is a target that I'm sending traffic to. So these are, so I have, foo.com is my service that comes in, and I route it to the UI. So I'll have a route that matches slash, foo.com slash, route it to cluster foo, and I'll select a pod IP address here. That's really what that upstream IP means, right? It's the load balancing set. And critically, in Envoy, when we get into things like circuit breaking and lame ducking behavior, Envoy actually keeps 2 sets of endpoints for every cluster. It keeps the active set, known good endpoints that I'm sending traffic to, and it keeps a, I forget what it calls it, the passive set or the non-active set or the evicted set, which are endpoints that I know about that belong to the service, but for some reason I don't want to send traffic to them now. Maybe they just gave me an error back, and I don't want to send traffic to something that just gave me an error. Or maybe the connection got severed, so I don't want to send something to maybe that died. But I'll keep it around because I can retry later, right? I can gracefully attempt to send a new request to that endpoint that failed before, and if it succeeds, then I can move it back into the active set. This is one of the key properties that makes the system resilient, right? Is that individually at the client level, based on the view of the network that a specific instance of Envoy is seeing, it can adapt how it's doing load balancing so that it's not sending bad requests that it knows are going to be bad.
That set of the whole idea is that we pushed by
Pilot, yes.
Pilot, right?
Mhm.
Now they put the other way.
No, so Pilot understands the state of the world and pushes it into Envoys. In theory, you could use Envoys connecting to Pilot to understand the state of the world. Pilot does not do that today. So Pilot ingests a model from the service registry, and it pushes that model to Envoy. Okay, sorry. So I know I'm throwing a ton of information at y'all fast, but we're light on time, so we're going. So Pilot is the piece that's responsible for configuring these envoys at runtime. Exactly like I said, there are two primary configuration sources for Pilot. The Istio configuration that you write, this is the Istio YAML files that you're familiar with, and service registry, service discovery integrations. These together feed into a universal model, which gets exported as Envoy configuration. Aggregated Discovery Service, ADS here, is one API that you can use to send all of the Envoy data. So it's kind of the superset of the listener, the route, the cluster, the endpoint discovery services. And sorry, one. And ADS is important because it allows you to sequence updates. So if I have 5 independent channels for different types of configuration, I have to do a lot of bookkeeping in Pilot to coordinate when I send what config to the specific sidecar. Having a single channel means that I can send it in order over the same channel and know that Envoy will apply it in order correctly. Yeah, so in this data model, the Kubernetes API server appears twice. It appears once as a service discovery or as a service registry. However, it also, in a Kubernetes deployment, acts as the configuration store for Istio configuration. Those are logically separate, but in Kubernetes, the Kubernetes API server acts as both. So it is typically the only service discovery that you wire up in Pilot is the Kubernetes API server, and then that is the config store as well. Does that make sense? One way in which you can augment the service registry or service discovery yourself is you can actually create an Istio object called a service entry. It turns out that is the thing that the model uses, and it's also an API that Pilot exposes directly. So suppose that my Kubernetes service discovery doesn't have google.com in it, but I need to call out to google.com. I might need to go create a service entry for google.com to allow the traffic to flow out. Yeah, and so that'll be stored in the Kube API server as part of Istio configuration.
Like the thing that tripped me up a couple of times when I first started doing this was that by default, the mesh won't let you talk out anything that doesn't have an XDS service.
Yes, and that's actually now a configurable option. So, and this is part of Istio's security posture. By default, if Pilot doesn't know about it, you cannot send traffic to it. So you can't just deploy a binary that starts talking to a random address. Pilot needs to know about the address that it would go to. You can disable this behavior now. That did not used to be a switch that you could turn off. But now you can turn that off, and Pilot will just pass, and Envoy will pass through an address that it doesn't know about. But that's a decision you need to make relative to your security posture, right? Do you allow a random service to talk to a random address, or do you curate the set of things that you can talk to, right? And maybe you're just doing that at the network level today. They can. So in most organizations, yeah. So Envoy you can plug and play here, right? So the only requirement if you're doing mixer things is that the Envoy image that Istio provides includes a mixer filter in it, compiled into the binary. So if you want to do telemetry and policy, you need a build of Envoy that includes that filter. Otherwise, you can bring your own Envoy. And in fact, all of the control planes, so just yesterday, AWS announced that AppMesh, their control plane, was generally available. Tetrate announced that we have Get Envoy. is a distribution that you can use to get vetted Envoy images, and like that just works with that mesh control plane. So you can use Get Envoy to deploy Envoy instances into AWS with their thing. You can do the same on GCP with their hosted Istio control plane. Envoys are pluggable, right? And the only thing that you're going to get caught is when you need specific filters. In today, the only specific filter that's required for Istio is Mixer, and if you don't use Mixer, you don't need it. Yeah.
So that's why currently if you do the Istio install, you will get a
Istio proxy.
You'll get an Istio.
Yes. So there's one other change that we make too. So let me be totally clear. Yeah. So if we looked at the images that get installed, it's not the upstream Envoy container for the sidecar. It is the Istio proxy container that uses the upstream Envoy image, except that we compile in our filter. And then the second thing that we do is we actually have an agent that runs beside Envoy. It's kind of sidecar to the sidecar in the same container. And that is what's responsible for starting up Envoy and making sure it stays running correctly, given Envoy's hot restart capability and that kind of thing. And primarily, it exists to provide bootstrap configuration. So Envoy needs a specific set of configuration at startup time. The agent there gives that. OK, so sorry, we got to go faster here. So so Pilot uses those APIs to push to Envoys. Pilot can group together Envoys based on the service. So logically, I don't care really how many instances of the screen app you have. Logically, there's one Envoy there that Pilot produces configuration for and shoves it down the channels for all of them. Right, so you can think, and the key here, the insight here, you can think about it in terms of services, right? This is a service. All the service instances are going to have exactly the same configuration. Or not if you choose, right? You can pick which things get what config. And Istio now has a piece of configuration called the sidecar configuration, and that's used to scope what configuration goes where. So if you wanted to, you could say that these two get different configuration, or you can say that those two don't get any configuration about each other, that kind of thing. So fortunately, it is eventually consistent. There are ordering guarantees now. So critically, in the old pull-based system, there were no ordering guarantees. Now Pilot actually can provide configuration in a specific order. This should never affect you as a user, except that you used to notice it because it would break things for a couple seconds until things became consistent. But now you just shouldn't see breakages that you saw before. And with that, let's dip into the traffic management lab. Let's skip this one real quick. Let's talk about the actual more interesting traffic splitting rather than ingress. Then we'll go into the lab because we don't have a ton of time. So one of the first examples that I want to give is subsetting a service. So this is something that comes up very, very frequently, right? I have my current version of the service. I want to deploy the new version. How do I do that safely, right? If I'm just using Kubernetes directly and I have one service that targets my deployments and I deploy a new version, what I'm going to see is Kubernetes will round robin traffic to it, right? So if I have 2 instances of my old version and 2 instances of my new version, Kubernetes is going to do a 50-50 traffic split, old and new. That could be OK. But chances are I don't want to just like deploy a new binary and let all the traffic in the world hit it, right? Instead, I would like to be able to control in a fine-grained manner exactly which traffic and exactly how much traffic hits that new version. So the first piece of Istio configuration that I can use here is what's called the destination rule. And one of the things that this lets us do is split up a service into pieces. And this one in particular says that I have 2 subsets of a service. I have v1.5, and I have version 2. And version 2 is an alpha. And these are identified by labels. If I look here, I have a set of pods with this version label, with this environment label. And here I have the second set. These labels that are what I can use to carve up and split up a service. If I'm in VM world, where I don't have Kubernetes labels, for instance, These are emulated via environment variables. So there are a set of environment variables that Envoy will capture locally and send to Pilot when it first connects to Pilot, if you're in a VM. And that's how you would establish labels in that kind of an environment. And then once Pilot has those labels, you can write a destination rule that splits those up. And one of the cool perks is Pilot doesn't really care where those destinations are, right? So like one subset could be on VMs and target VM-based workloads that are connecting to Pilot. Another set could be on Kubernetes. It doesn't really matter as long as the network connectivity is there to allow them to communicate. Then, so rather than doing our naive, if we have 4 of these and 1 of these, then Kubernetes is going to do 75% here and 3 of these and 1 of these. It's going to do 75% here, 25% here. If instead I want to do a gradual rollout of the configuration, I can say only send 1% of the traffic to my alpha and send 99% to the rest. And that's done on a per request level, right? So not per connection, per request. Unless you're dealing with TCP, in which case it is connection level, because that's all you can do. But it's sort of like percentage base is cool, right? But that is typically, and that's a very useful tool. But oftentimes, I actually want to target even more specific sets of traffic. So it's not really that I want 1% to go somewhere, but maybe I want all of my internal users to hit the new version of the service before external users hit the service, right? Or I want some other feature of the request to trigger that you hit the new one rather than the old one. So in this example, we can actually use the user agent that comes in. And so we can say, hey, if you're on iPhone, you get the canary. And if you're anything else, you get the old one. So now I can incrementally roll it out to a specific set of users using request metadata. This could also be things like network ranges, right? So I can say, hey, if you're coming from this subnet, you get this version. But all the other traffic gets the default version, right? So any of the static metadata, any of the attributes that I can extract from the request, just about, I can use to do this routing. Critically, this routing happens locally at Envoy. It doesn't go to Mixer. It doesn't go anywhere else. This stuff gets manifest as routes in Envoy, and those decisions happen locally about where this traffic goes. So this regex on the user agent is evaluated locally at Envoy to determine which cluster, which route applies. And so with that, let's go dive into some of the traffic examples.
How does this work with Kubernetes service?
Yeah.
Does this still go through proxy?
No. So the question is, how does this work with Kubernetes services? The answer is that Istio entirely ignores Kubernetes services because I don't want Kubernetes load balancing, because Kubernetes can only do round robin. And so if I had to take the sophisticated load balancing that I'm doing and then shove it through a round robin layer of load balancing, the only load balancing I get is round robin.
But it does use the services for service discovery. Right?
Yes. So critically, what happens is in Kubernetes, when you create a service, that results in a DNS name and a virtual IP address being allocated. When your application tries to call a Kubernetes service, it'll do a normal DNS resolution, and that will resolve to the virtual IP address of the service. That is the IP address that Envoy sees when, right? So normally in Kubernetes, you would forward to that IP address. Kuproxy would capture that and decide on an endpoint, and that's where it does round robin. Instead, Envoy captures that. It sees, oh, this VIP belongs to that service. That service has these 10 endpoints. I will select an appropriate endpoint among the 10. Right? Does that make sense? But it totally bypasses the Kubernetes routing layer there. Yeah, no, please.
Importantly, I think the thing that's really important to clarify is that the IP table rules for the service can still exist, but they will never be hit because the traffic will never exit the pod going to the VIP that the IP table rule is going to pick up.
Exactly.
Whereas Envoy will pick it up and say, and instead direct it directly to the pod where the traffic
With a specific IP address of the pod, yeah. So again, just to reemphasize here, when Envoy intercepts that traffic, it picks a specific destination IP address. Kubernetes does not have any IP table rules for specific pod IPs, right? It only has rules for service VIPs. So we totally bypass how Kubernetes does the traffic capture to route traffic. All right, so let's move over to some of the traffic management stuff so we can actually play around with the system. I will say it's very helpful if you have at least Grafana open in the background so that you can actually see your traffic changes affected.
So you skip the ingress section as well.
Yeah, so sorry. So let's just skip the ingress section for now, and let's go right into the routing section, because that'll be more interesting for us. The answer for the ingress section is that I cheated and I already had you install the ingress, and that's why you can go to the web page. If we didn't install the ingress stuff there, then you wouldn't be able to navigate to the UI page that we went to. So go look at that to see how some of that ingress stuff works. And you can always email questions afterwards. But instead, yeah, let's get into the routing. So again, if we look, so what we want to do is traffic splitting, right? So I have two versions of my user pod running. And what we're going to want to do is split traffic across those in a controlled way. So the first thing that we need to do is, again, tell Istio that these are two separate things. So here's the deal. If we get services, we see that there is just a user service. Sorry, let me make this a little bit better there. OK. That user service does not differentiate between version 1 and version 2, right? So if I just start to send traffic to that service, I'll get half the time I'll get v1, half the time I'll get v2. And in fact, we can see this in the UI. If we go here, I hit version 1. Hit version 1. We're getting round robin not very well. I didn't actually apply any rules, right? Oh, that's funny. But this will change as we hit version 1 and version 2. Does the service by default only route to, where's Liam? I don't see him. He was the one that wrote this. I think the service by default only routes to 1, but we'll see. OK, beautiful. That's what it should do. So what you should see is that every other reload about should hit one or the other. I don't know why mine is not. That's always fun. Oh, there we go. It's because I was hitting the wrong page. So there. We can see in the top corner. But notice it's not actually precise, right? But with Istio, we can actually make this precise. So the first thing that we'll do is create a destination rule exactly like the one I showed you in the slides, right? So I want to take the user service, and I want to split it into two subsets, because I know that I have two of them deployed. Here I can see that I have two deployments of the user service. And so this destination rule will make Istio aware that there are two different subsets, because today it just blindly thinks, like Kubernetes, that there's one, because that's the only service that exists. Oh, whoops. Sorry, wrong window. Great. Given this subset, we can now create a virtual service that controls how things are routed. So from our ingress, if we had done the ingress lab, one of the things that we would have learned is that the user service is accessed on the v1 user's prefix. If I go here, I should be able to see this in the, no, it's accounts, sorry. And with this prefix, this is an example of a match of a route that we can write. So I can write matches on arbitrary prefixes, for instance, and I can route them to specific destinations. In this example, I have two destinations, version 1, subset 1, v1, and subset v2. And today I'm saying 100% of traffic goes to v1. None of it goes to v2. And then if we come here, what we should see is never a 2, right? If I sit here and refresh this all day long, we'll be pinned to 1. Great. So we can then go and make this incremental, right? I can say for some specific set of percentages that I want to pick, I can come in here and I can say, hey, let's route to 75%, right? We can do a 75-20 split. Right, and so I just did a kube control edit, so this is actually editing the live YAML. Never let your developers do this in production. And then if I'm really lucky, the 4th, 5th, 6th, okay, there we go. So we saw 2. So I had to refresh 5 times. There we go, we got a 2, right? And so what we should see is in aggregate, I'll land at 25%, 75%, right? It's important to note though, one tripping hazard that really only ever comes up in demos is that we only have one client here. So keep in mind that in a real world system, this decision 75-25 is done across all requests that are incoming. So it's kind of boring because I'm one client, so I can kind of see what's happening. When you have many clients for real, you're not going to be able to see from your perspective from this one browser. I may not get a 25-50 split, or 25-75.
We should be able to pull up that data.
Exactly. So if we go to Grafana, exactly. So if we go to Grafana and we look at the user service, I can actually split this out by version. Let me see, yes, here we go. So here I can actually split out per version all the data, right? So incoming requests, response codes, I can see is version 1 and version 2 are both only returning 200s. I can see that they're both 100% successful, the relative latencies of the two. All of this data gets broken down per version. Let's see. Okay, so this depicts targets. And then I can also, by the way, drill into specific subsets, right? So I can look at the stats for only V2 of the service. Or I can look at the stats for only V1 of the service, right? Or any number of subsets. And yeah, and so my point here being, so we can see the nice traffic here because we have one client. In general, you're going to have to see metrics to prove that your traffic split is actually doing what you think that it's doing. And again, we have nice blocks because I don't have continuous traffic being driven in the background, right? Finally, what I want us to do is look at some of the traffic splitting. So I can do Chrome versus not Chrome. Is another easy one that we can actually show here, right? And if I go look at this gateway that we just created, or this virtual service that we created, what this does is it says, hey, if you're going to users and your Chrome, go to V2. Otherwise, if you're going to users, go to V1. And now what we should see is go from me never seeing a V1 or seeing it very infrequently to only seeing V2. And if I pop open Safari and oh, go away, Safari, stop. Oh, God. You can tell that I never use Safari. And I log in. I should see that I only ever hit 1, which is true. But here in Chrome, right, I hit 2, right? Okay. And again, I want to emphasize that we can do this on all of the statically accessible features of the request, right? So right now I'm showing you I'm showing you traffic splitting, doesn't require on any feature of the request. We've been showing you user agents and path-based matching, but I could just as easily use CIDR ranges and specific IP addresses instead if I wanted to, for instance.
Sorry, for the IP, the one way is the regex where you understand the CIDR.
Yeah, so you can. So we understand CIDRs. You can give a /32 if you want a specific IP address, but it's not a regex. There's actually you would say match source IP address, and you would give the range. Yeah, exactly. Yeah, so just it's a standard, whatever /CIDR range. And you can put in an explicit IP address, and we assume that it's a /32. And then the final thing is we'll just go ahead and reset our traffic routing back to normal. And if after doing that, what we should see is a nice even mix 50-50, 1-2. Because all we did is removed what we had and restored our Kubernetes behavior. Okay, let's touch on resiliency real quick. because again, we have about 45 minutes left, and I would like to get into some of the security stuff as well. And after this, we'll take like a quick 5-minute break just so everybody can breathe. So one of the really interesting features that Envoy has is the ability to inject faults. And this is really cool because typically to see what happens when our system behavior degrades, we have to have an outage. And that's maybe the worst time to see what happens when your system, or let me rephrase. Most of the time when our system degrades, we are having an outage. And the impetus is on fix it now, right? It can be very hard to understand how the system would behave given a specific failure condition, right? Setting up reliable tests so that you can track your service behavior regressing over time with respect to particular kinds of failures is very hard to set up and do reliably in a lot of environments, right? So we can actually use Envoy to emulate faults in our environment for us. And what that means is that we can start to build more reliable testing infrastructure in the presence of faults to test. So what happens, for example, if I specifically force half of the traffic going to a specific service to have 500s? How does the UI behave? How many people can tell me now what happens to their main web page when their auth service has an extra 2 seconds of latency over normal? I don't know. Like, it's hard. What happens when it's not the auth service, but it's like 5 dependencies down from the auth service that we have the delay? Right? Understanding this kind of dynamic system behavior is incredibly complicated. And being able to inject faults in a reliable way in other environments gives us an incredibly powerful tool for understanding how our system works. So let's go ahead and set that up. Great. And how is this actually going to manifest as a failure? I suppose if I read the training material. There we go. Yep. So hey, it worked, didn't work, right? So here's our UI does not show an error message. Instead, it fails gracefully and just shows empty data. And if I come here, we applied this to the accounts. I should be able to see some 500s somewhere. Do we not show faults? Actually, we don't show faults in metrics, right? There's a catch here. There's a gotcha. Faults are actually happen client-side, not server-side. And client-side reporting is disabled. So when faults are injected client-side, you actually don't see the failures now. That's a new feature of Istio 1.1, which disables client-side reporting.
I mean, if we turn on both sides, can you do what we do?
Yes. Yep. So by default, it dedupes. But it's so, in my opinion, having both sides is very valuable because you can see the delta between client-perceived latencies and error response codes versus server perceived. Great. So we have failures. So given that we have failures in our system, what are the tools that are available to help mitigate the user experience of these failures, right? So this, I would argue, is a pretty unacceptable experience. If I logged into my bank account and I just saw no accounts with zero, and no balance in them, I'd be pretty upset, right? So clearly this is not behavior that would be acceptable. So what are the tools that exist to help us remediate this? And Istio provides a variety. So the very easiest thing that we can do is go and apply retries, right? So these are independent processes. Every request is independent of the other requests. So if I say attempt 5 retries on an endpoint that might fail half the time, what I should see is that it only fails about 3% of the time, right? If these are truly independent failures. Because I'm the one that's injecting the failures, I know that they're independent because I know that Envoy is flipping a coin every time I make a request. So if you do the math, 50% 5 times is 3% failure. And so if we go apply this and refresh the UI a bunch, we shouldn't see failures. What we should see instead is that some web page loads take longer than others because I'm sacrificing latency for availability. I'm retrying my connection and delaying the UI load to retry against other backends that might succeed where the other one didn't. And so that one worked. We're actually going pretty fast. So here we are still getting some failures. That was statistically very improbable.
Does it assume that the application is identical?
So in these, yes. So as far as retries go, you can set pretty extensive conditions on the retries, including specific error codes and specific methods. But in general, yes, the assumption is if you're going to do retries like in this manner, it assumes that it's idempotent and fair to try across different servers. And in fact, that is how Envoy is implemented. So when we send a request and it fails, the retry is guaranteed to go to a different endpoint, so long as other endpoints exist and you're not in panic mode, is what Envoy calls it. So if I know no good endpoints, then Envoy goes back to sending it everywhere because everything is going crazy. And so short of that scenario, yes, retries will always go to a different endpoint than the original request was sent to. Because if you just retry against the same server, you're going to fail multiple times and you're not doing anything.
But it can go like a different version, right?
Yes. So it'll literally, so if we talk about the Envoy config endpoints, it'll pick a different endpoint, so a different IP address to target the request to. Sorry, here we go. This should be the, sorry, I didn't actually apply it. Now we should not see failures. It would be incredibly statistically unlikely for us to see a failed load, but there we go. 3% chance we hit it. Reading it a lot. There we go. All right. Sorry, I want to make sure that we actually have this set up correctly. Yeah, okay. Yeah, okay, oh, I'm sorry. So we changed this down, so this is only 3 retries. So we should actually see a failure about 10% of the time. 12.5% of the time. And again, these are because they're independent processes. So this is a very, very small sampling of the kinds of network control that we can actually do in Istio. If you go look at the reference docs, these are the source of truth for all of the configuration in Istio. In particular, if I go over to the traffic management bit, we're looking at virtual services. And here, for example, I can look at, let's see. So like here are the various ways in which I can match HTTP traffic, right? I can match on URI, on the scheme, on the method, on the authority, on the headers, right? If I go look at, for example, TCP, I can match on the SNI, the TLS connection gave me. I can match on ports or source subnets, that kind of thing, right? And over time, as Envoy supports more and more protocols, you'll see more and more of these things appear. And so with that, let's take a break and let's try and be back at noon for the final security bit. Or do we not want to take a break and keep cruising through to security? Keep going? All right, awesome. If you're, well, some people are leaving. What do we show? Okay, we'll keep going. We're short on time. I would like for us to be able to talk through this because this is some of the interesting things. So again, in the security, we're going to talk about how we issue identities and authenticate them, how we then use those authenticated identities to do authorization of service-to-service communication. It's a mouthful. We'll also talk about how we use those identities to do encryption in transit. And that encryption in transit is actually a very important part of how we authenticate. And then finally, we'll talk about the actual PKI that Istio ships. How do we manage these certificates? How do we mint them? How do we rotate them? How do we make them available to workloads? All that stuff. No, that's exactly what I just said. Hey, nice. All right. So in Kubernetes, Kubernetes as a platform already allows for workloads to be assigned an identity. In Kubernetes, this is the service account, right? And that is the runtime identity that a pod presents. Istio, because that is the platform default, Istio takes that and uses that as the identity that it mints for the service at runtime. That identity that is minted is created according to a spec called SPIFFE. And SPIFFE stands for Secure Production Identity Framework for Everyone. And really, What Spiffy does is describe a naming convention that's universal. It's based on a URI, so it's a path. Spiffy, the spec, describes how you take that identity and encode it into different documents. The one that we care about is an X509 certificate. And an X509 cert, again, is the certificate that you would typically use to do things like SSL termination, right? So I have an HTTPS website. I go to Let's Encrypt, and they give me a certificate. That certificate that they gave me for my website is an X509. We use the exact same ones, and Spiffy says, when you construct an X509 certificate, fill in these specific fields in specific ways. And if you do that, then when you do a normal certificate validation, so there's a well-known way that we do PKI path validation, is what it's called. So we validate a certificate as valid. If you do one more step while you're validating that certificate, then you can authenticate the identity inside of that certificate. That is the guarantee that Spiffy makes. So Spiffy says, if you have an X509, and you handle it this way, and you authenticate it in a standard way, and after you've authenticated it in the standard way, you check the subject alternate name, then it is a valid Spiffy identity. It has been authenticated. And so this is the promise that Spiffy makes. If you do that, if you meant it this way, if you validate it that way, it is an authenticated principle. So what do they look like?
It's very much like the TLS connection.
So we use it in TLS. So at runtime, we take these certificates and we do mutual TLS. And that is how we do the and envoys are modified. So when they do that TLS handshake, they will do the extra little bit required for Spiffy validation. And those principles, those authenticated principles, both source and destination, are then made available for policy. And so I'll talk about that in a second. So like I said, Spiffy, they're URIs. The scheme is Spiffy. The host is your trust domain. In Kubernetes, this is the local cluster. In an organization, that may be the organization name, right? So I may say that Tetrate has one trust domain. I don't care what cluster you're deployed in. Tetrate is the root of trust for all the service accounts running in Tetrate clusters. So my trust domain should be tetrate.io or some internal DNS, or some internal name, right? And then the path could be anything that you want. But the path is what really encodes a specific identity. So you can do, for example, a UUID. If you want I want to mint a unique name for this thing, cool. When it comes to Istio and issuing identities on Kubernetes, we use the Kubernetes service account as the identity, and we encode it as a path in the URI. So we say this cluster is your root of trust, and in the staging namespace, you have the default service account. That is how we read that identity that's issued to the workload. So the default, so any pod in my Kubernetes cluster that's deployed into the staging names, that's deployed using the default staging service account will receive this identity. Because in Kubernetes, when you gave it that service account, you said this is the identity of this pod. And yes, so if I have 10, yeah, so as long, and so that's why I made that point. So as service accounts are assigned to deployments, and I can have many replicas that have the same identity, right? So that deployment can all share the same service account. So if I have 10 replicas, those 10 will have the same identity. Now, because it's an arbitrary path that we pick, we could choose to issue a separate identity for each of those 10 if we wanted to, right? And the way that we might do that is to encode the service account like this, and then do /pod ID. So today it is not configurable in Citadel, but that will be one of the extensibility points that is coming soon, is the ability to choose a custom Spiffy identity format. But today it's hard-coded to be the Kubernetes service account.
Zach, how many times this operation is happening? Like normal application, making the service call. So how many times this identity verification and establishment? I mean, is it on per call?
Yeah, so it's per connection. Yeah. So we actually do the authentication of the principal via the TLS handshake, So that is once per connection. So we don't have to redo it per request.
Okay, so once the connection is established
Yes.
between the pods,
Mm-hmm.
it should be 1.1 connection, I suppose.
Or 2 or whatever. So like Envoy, for example, will do upgrade to 2 from 1.1, right? But yes.
And then it just lives till you tear down the pod.
Exactly. But that will be based on what your application is doing, right? So if you're tearing down the connections, we'll tear down the connections. In general, though, Envoy will try to keep connections open as long as it can. And so you pay this cost. And it's not really like the additional step that you have. It's normal PKI validation, right? So it's normal cert validation. If you have hardware offload, you're going to do the hardware offload. That's all fine, right? And so that's no more than you would pay if you were terminating TLS normally. The one additional step is just checking the subject alternate name in the certificate. So we call this document an SVID. That stands for Spiffy Verifiable Identity Document. Spiffy, the spec defines how names work. Spiffy has a separate spec for each document type. X509s are one document type. That spec says, here's how you make an X509 cert that is a Spiffy identity. So once we have those identities, and we'll talk about how we get them to the workloads in a minute, but once I have those identities, I want to write policy using them, right? So just having an authenticated identity doesn't do me any good. I need authorization that uses those identities. And so just for recap, authentication is verifying that an identity is true, right? Are you who you say you are? Authorization is answering the question, now that I know who you are, can you do the action that you're trying to perform, right? And so we need both together. In Istio, we're only talking about services. So you and the object are both services, right? The you is the source service. The object that you're accessing is the destination service. And the action that you're performing is what is the request that you're making, right? Are you making a read? Are you making a write? In HTTP, we would encode that as like a put or a get or a head or a write or a delete or whatever it is. And so Istio doesn't answer the general access control question. It answers the specific access control question. Can a service perform that operation on a target service? So the question is, how do I write that policy in Istio, right? So I want to enforce authorization policy. How do I do that? Istio provides RBAC as the method to do this. So role-based access control should be something that we're pretty familiar with. And so the way that it works is first we define a role. This is a set of permissions to do something to a service. So this role says that you can do get and head HTTP requests on the PII service. It's not assigned to anyone. It's just it's a set of permissions that exist. I can then take that role and bind it to an identity. And this is what actually is a policy that allows access. So what this says is the identity of my case tool, and I'll show you an example in a second that hopefully will put some of this in context. But this says that my case tool can, with a valid JOT token, with the correct claims, because we can do both the MTLS identity, and then we can also verify a JOT token that's passed in the channel, that's passed in the request as well. So that says if you're from the case tool and you have the right JOT, if you have the right ephemeral credential, then you can have read access to that PII service, right? And note here, this is this name, PII reader. It is exactly that name that we use here.
So is this a cluster role that's got a local namespace binding?
Kind of. So yes, the roles are cluster-wide. You need to reference them by their namespace. So I didn't mention this, but see here, this is a namespace default. This is a namespace default, so I can use the short name. If I was in a different namespace, I would need to use the fully qualified name of this role. But roles are visible across namespaces because I want to be able to do things like, as a service owner, produce a set of roles that allow access to my service. And as service consumer, I should be able to write bindings for, and those could live in the consumer namespace if I wanted them to.
You're saying that JWT token is for like could be for a real life end user.
Yes.
For authenticating.
Yes.
Do we have a way to authorize based on details in that token?
Yes. So Envoy, and that happens locally in Envoy. So the authorization decisions in general go up to Mixer to decide. It's a type of policy. However, JOT claims specifically are processed in Envoy. Envoy has a filter that decodes and accesses JOT data. And so yes, this is a very important thing to highlight, thank you, is I am coupling user and service identity together here in this policy. If you're coming from this service and your ephemeral user token, your JOT, has the right claims, I allow access. That's huge, right? So I'm not saying anyone using the case tool can access the service. I'm saying anyone using the case tool with the correct ephemeral user credential can access. That's fundamentally different, and that's huge.
But that's how you can only do one of the, right? Whether you can do the JOT or you can do the TLS.
No, both. So I'm doing both here. So this spiffy identity is only available in the mutual TLS connection, right? Because that is how I authenticate we'll talk about mutual TLS in detail, but the only way that I can authenticate the credential is doing the TLS handshake. And so this is both. So at the connection level, we establish our spiffy user, and then per request, we'll extract that JOT and check its claims.
Isn't that redundant?
No.
Because you're doing two-way handshake, you're two-way identity validation. That means you have positively provisioned the clients as well.
Spiffy does not require that these be in the same trust domain. I can very easily set this up across trust domains. Secondly, suppose that the way that you access the case tool is via the ingress UI. So now now it's a policy on ingress and not on a specific user of the tool, right? So this is coupling users of the tool. So if you're the tool, and and as the tool, you've gone out and gotten the JOT and attached it to the request in behalf of the user in context, then you can make the call, right? So it's the coupling of service and user identity. This could so today Envoy doesn't handle OAuth, but you could imagine OAuth instead of JOTs, right? And then you could say if the OAuth credential is valid, OAuth doesn't, if it's valid and has the correct scope codes, right? That's the equivalent of a claim, a JOT claim, and OAuth scope code. If it has the right scope codes, allow it, and that would be effectively the same. So we have a lab for time right now. I'm going to skip the labs and we'll do the content, and then we'll go back to the labs to finish up because we only have about 20 minutes or so. So let's talk about encryption in transit. So I've been talking about TLS a whole bunch. Hopefully people know what that is. If not, you're probably familiar with SSL. TLS is the new name for SSL. And it's the secure part of HTTPS, right? So if I'm doing secure communication in general, it'll be over TLS. Traditionally, when we do TLS, it's one way. So the way that you traditionally experience TLS is in my browser, I go to google.com. And here, look, I have a little lock, so I know that I did TLS. That's great. And I can actually go, if you're crazy like me, occasionally you'll go to a site and you'll actually look at the certificate because you want to see if it's real or not. And so here I can go and see that this is actually like a valid Google cert. But I didn't give Google any proof of my own identity in this, right? I just made a request. This is where mutual TLS is fundamentally different. Mutual TLS requires that both parties provide certificates to each other so that I know the client that is talking to me is the server, and as a client, I get the same traditional trust that the server that I'm talking to is valid as well, right? So the reason that we do one way in web is because typically a web server serves many clients, and we don't care that the client is trusted, right? I handle that in a different layer. I handle that in the application itself. But when we talk about service-to-service communication, I control both ends very well. So I want strong identities there so I can do mutual TLS. This is the advantage of using spiffy X509 SVIDs. You need some secret to do mutual TLS with. Because we already have certificates laying around encoding our identities, those are the ones that we use. And because it's spiffy, because I use them to do the MTLS, I know that it's an authenticated principal. when I extract that data out of the channel. And again, so there's benefits to doing TLS2. You get the traditional benefits that TLS provides. So you can do things like forward secrecy and that kind of stuff that just automatically works with TLS. All right, so this walks through a little bit of the demo. So when I start to apply policy around which services can communicate, it's typically I don't know which ones communicate a priori, right? Like if I just go ask my developers, hey, for this service, hey, what does your service talk to? You're probably going to get a different set of answers for every single developer that you talk to, even though they all work on the same service, right? They're all going to have some subset. So it can be very hard to go and apply policy holistically. Oh, I'm sorry, this is mutual TLS policy. Let me get that first. I'll get to RBAC policy later. Sorry, I'm skipping ahead. So for mutual TLS, we have a timing problem. So suppose that I want to enable mutual TLS across my deployment. I want to start doing this policy. You have a chicken and egg problem if you're going to do mutual TLS, which is a connection is either mutual TLS or it's not, and a client attempting to connect to a server via mutual TLS where the server is not accepting mutual TLS doesn't work. And a server attempting to serve mutual TLS where a client wants simple doesn't work. So that means that if I want to, naively, if I want to just enable mutual TLS in my deployment, I have to redeploy client and server in a coordinated manner at the same time. That's clearly impossible. That's ridiculous. We just can't do that reliably and effectively, and certainly not repeatably. So fortunately, Istio has a graceful mode where I can opt into mutual TLS, and we call this a permissive mode. So what I can do is for any particular namespace by namespace, or across the entire cluster, I can set policies around which things are allowed to communicate and how they communicate, whether it's via mutual TLS or simple TLS. In this case, what we want to say is we'll do a permissive mode. And you would use a permissive mode while rolling out mutual TLS. And what this says is if a client tries to connect to me with mutual TLS, I'll serve mutual TLS. Otherwise, I'll serve simple TLS or nothing at all. And this is a feature in Envoy that we can do. So on a single port, we can do this. We can choose how we handle the certs. And what this does is it decouples client and server rollouts when I'm doing mutual TLS rollout. So now my server, I can turn on permissive mode, and I can provision its certificates. Now, if a client does mutual TLS, it'll happily accept it. If a client does simple TLS, it's fine. Then I can go to my clients and roll out mutual TLS there gradually. And we can do that service by service, right? And my service probably has a bunch of different ones that call it. I can do that per caller gradually and slowly opt in, and it'll work, and they shouldn't notice. It's a cool feature that was added relatively recently. I think it came around in Istio 1.0. And before then, turning on mutual TLS was a destructive operation. You did it at install, or you didn't do it ever.
It's another example of operational continuous triumph security.
Yes, it is exactly that. No, it's exactly that, right? But the thing is, if I came to you and said, hey, the only way your system can be secure is if you take everything offline for 5 minutes. That's clearly not an answer. Yeah. Right. And so this way we can opt into it gracefully, and so we can move gradually to a correct security posture. And once we're in the correct security posture, we can disable permissive mode. And I can make it strict. I can say you can only connect with mutual TLS, no permissive. And now when new clients come along, they must do it. Right? So this is a tool that we use to opt in gradually. And then once everything is opted in, we can turn it off and not allow opt-in anymore.
In the case where you're doing strict mode,
Yes.
and one of the services is exposed by the ingress gateway.
Yes.
The ingress gateway created an identity for external.
This stuff only applies inside the mesh and does not apply to ingress traffic. So in that scenario, ingress will terminate traffic however you configure the gateway. We skip the ingress section, but there's also a security ingress section. We talk about how you terminate TLS at ingress, right? That's the common thing. If you have mutual TLS turned on like this, then the ingress proxy will re-encrypt into your destination service. And the certificate that it uses to re-encrypt will be the mesh certificate and not the public internet-facing certificate. Yes. So this is actually namespace scoped here. So this says only in this namespace is it permissive. So you can start to do this namespace by namespace if you would like. You can start to lock it down with the correct security posture, namespace by namespace. Yeah, so yes. And there's also cluster-wide versions. I do not believe that Istio allows that today. It does allow opt-in to mutual TLS per service, but I believe that those are all done at the producer layer, not the client layer. So it's the service owner says, you can do mutual TLS to me, but it's oblivious to the client. So no, it does not, at least as far as I'm aware.
But this is on the server side, right?
Yes, yeah, so that's what I'm saying. Yeah.
Other namespace, it's probably not there, right? Whether the request comes from.
Yes, so exactly. So with the way that it works today, the server doesn't care what namespace the client is in. It applies the same policy regardless. Yes. And so this is why, or this walks through how we can do safe TLS enablement, right? And where the actual policy applies, right? So if we do things like JOT-based security, that applies at the application level or above, where channel-based security, right, is yeah.
So, sorry, I think you implied this before, but I just wanted to.
Yeah.
So, is it possible to use the service role binding, where the service role binding uses only the JOT token and not the
Yes.
not the service identity of the.
Yes. Yes. So yeah, so you can write service auth policy over users. So you can abuse the service auth to do user to service auth if you really want to. That's not really the intended use case, but it does work.
Yeah. I would only do it in an active way.
Yes. Instead, if you wanted to validate user credentials in Istio, and that is a thing that in my opinion is worthwhile to pull into the mesh, because today you likely have it implemented as a set of client libraries. And so now you have to maintain these client libraries. You have the library update problems. You have the polyglot problems. So that, in my opinion, is one of the best policies that you would like to pull out. You would typically do that as a mixer adapter, right? So you would extract some request, some bearer token, for example, from the HTTP headers, or some other token like that off of the request. You send it into Mixer. Mixer does its validation against your, OICD backend or your LDAP backend, and yeah, it nixes the request or allows it.
Is that for authentication or
For Auth-Z, right? So if you wanted to tackle user credentials rather than purely service credentials, I would recommend, rather than doing it via like JOTs in the Istio RBAC, you should instead probably implement a Mixer adapter against your existing auth backend.
The reason I asked is that we currently have a precursor to this sort of thing that uses JOTs for services.
Oh, gotcha.
So I'm trying to figure out how to make that work.
Totally. Fun. Okay, so in the last 13 minutes, we will talk about the simple subject of certificate rotation. So fortunately, there are some things you can actually do to make certificate rotation simple. The best thing that you can do is just automate it, so you never have to worry about it. And then you do it all the time, so you don't worry that it breaks. And there's a bunch of other benefits. So if you actually go read the SPIFFE SVID spec, it does not mandate how long certificates should be issued for, but it does recommend that when you issue an X509 certificate with a SPIFFE identifier, that the time to live of the certificate be short. I think it uses explicitly the word short and does not give any more than that. What we mean by that is traditionally when you go to like Let's Encrypt to get an HTTPS cert, that lives for a year or 3 years. That's the traditional TTL that we assign. Instead, I want to assign a TTL of like an hour. Right? I want very ephemeral credentials. And the reason is that this bounds so the service policies bound an attack in space. Right? So I set up authentication policies around which services can talk to which other ones. That bounds an attacker, their ability to attack other services to just the set that my RBAC policy allows. An ephemeral credential bounds the attack in time. right? So if my cert lived for a year, an attacker could gain access to my system, steal the certificate, hold onto it for later, and then come back and attack, right? If instead that certificate is only valid for an hour, then an attacker has to continually re-steal the certificate to continue to perpetrate an attack. So authorization, service policy allows you to bound space. Ephemeral credentials allow you to bound an attack in time and makes the method of attack substantially harder because you have to continually reacquire credentials. So how do we handle this? And the answer is there are 3 moving parts in the system that handle the certificate issuance and rotation. The primary piece is Citadel. This is the piece that looks at the Kube API server, monitors for service accounts being created, and mints certificates for those service accounts. On every node, there's an agent. When a pod is scheduled onto that node, it communicates with the local agent and says, hey, I just got scheduled. I want my identity, please. And the node agent goes up to Citadel and says, hey, this pod was just scheduled. I would like its identity, please. And Citadel does its checks and issues it down. If we look inside of Citadel, this is about what it looks like. So the node agent exists on the node. A workload is deployed, talks to the node agent. It goes through that API and into an authentication. So I need to authenticate that the node agent requesting the identity is valid. We can think of this as an environmental check. So to issue an identity, I said originally, if I want to issue an identity, I should validate to a workload. I should validate that that workload is in the correct environment and that the workload itself is correct, right? I don't want production identities in our test infrastructure, and I don't want dev binaries running in production. So this node authenticator acts as our way of validating the environment. So the node at Bootstrap, when it connects to Citadel, has to prove itself to Citadel in a way that allows Citadel to authenticate that the node agent is good and trusted. And we can talk about this. This varies per platform. There's some details we can go into how this works. Traditionally, this works by a cert on the machine, right? So if you're on AWS provisions a machine cert. You would typically provide that machine cert to Citadel, and Citadel would trust that as proof that the node agent is valid, right? Then, as a workload is scheduled, the node agent will ask for the identity. This goes through an approval step, which hits a registry, right? So I need to know which services exist, which identities exist. That feeds into, this is an authorization system, right? So Citadel itself is doing authentication, and then it's authorizing and then issuing an identity. Effectively, the node agent issues a cert signing request to Citadel, and Citadel signs those certificates and responds with it. And then the node agent communicates locally with Envoy over a Unix domain socket using Envoy's secret discovery service API, the XDS API. A really cool benefit of this is that the certificate is never written to disk. It is only ever handled in memory, right? So Citadel mints it in memory, hands it over the secure channel to the node agent. The node agent hands it over a secure local channel to Envoy, and Envoy only ever holds it in disk. Only ever holds it in memory, never on disk. This is a great benefit. I can't accidentally leave a machine in some half state and somebody come along later and recover those certs. An attacker would have to actually read the memory rather than reading disk to see things. That's way harder. Or not if you're doing Rowhammer. A variety of side channels.
Is Envoy making the certificate request or generating a
No.
certificate, or it is saying, give me a certificate, and Citadel is doing the whole thing and giving it?
So the node agent is doing a certificate signing request. Envoy Envoy at startup, part of the Bootstrap configuration of Envoy, we say, hey, connect locally to the node agent for your certificates. And when that connection is established, the node agent does some authentication there, and then that channel remains open, and the node agent goes, retrieves certs, and gives it back over the channel, and uses that same to rotate the certs.
Okay, so who is generating the key pair? Is it node agent or Citadel?
Node agent is generating the key pair, and then Citadel is signing that key pair and issuing it.
So you have a replica, and every replica will request their own certificate.
Yes. Yep. And the node agent caches those, right? So if those replicas are landing on the same physical node, then I would hope they're not. But if they are, those will be cached. Otherwise, so each node agent will go and caches the set of credentials for the pods on the node. Yeah, so continually, so node agent keeps track of the credentials that it's issued on that are live on the node and handles going back to Citadel, asking for new certificates in a timely manner, and then pushing them to Envoy. Yep. Yeah, totally. So today, Envoy is written, or today it is configured such that Envoy closes the connections that are open to it when it receives a new certificate. This is an option that we choose. It's not required because an open transport with an expired certificate is valid, right? You never recheck the certificate after you establish the connection. So we could leave those open, but as a security posture decision, it was decided that you would close them. And again, this is about bounding attacks in time, right? So if I don't close that connection, then I can use an invalid cert and keep that connection open for forever. So you want some amount of churn to ensure that things are staying up to date.
Because in this case, Envoy does not become closed when it gets a new certificate on the
Yes, exactly. And so yes, so if you sever, and there's graceful, so the other thing is that Envoy has graceful draining of connections, right? And so what actually happens is that Envoy spins up new listeners on the same ports and gradually shifts traffic over. Right, but yes, if you have some super long-lived TCP connection that is a session state, that you do lose that session state, and that's an intended consequence of the design. That is something that could be disabled, and I think in the future we'll probably see things like disabling it per service, because there are definitely workloads where I would need that or not. Right. So the runtime dynamics. This should look fairly familiar. Pilot pushes configuration. Citadel talks to node agents, which talks here. The reason I want to highlight, there's a very important thing to highlight here, which is Pilot is responsible for secure naming. So Pilot is responsible for talking to the Kube API server and figuring out what service account this Envoy is supposed to run as. And at Bootstrap, Pilot pushes in I mentioned that there's an agent next to Envoy that takes Bootstrap, that gives Envoy the Bootstrap startup config. Part of that Bootstrap configuration is the identity that Envoy should be running as, because we go and get that from the system. So today, Pilot is involved in secure naming. This is actually pretty undesirable because it's a totally external component to the rest of the PKI system, and it requires that Citadel and Pilot coordinate with each other on naming. So in the future, we'll see secure naming move into Citadel. But at least today, as of Istio 1.1, secure naming is actually the responsibility of Pilot, and that happens at startup for Envoy. So here is a summary of what I just talked through. Here is a picture of what I just talked through. And there should be more data. Oh, this is the last slide, and we have 3 minutes left. Beautiful. So questions, comments, concerns?
So how do you deal with the network replication in the case of a certain rotation for
Yep. Yep. So that's a phenomenal question. How do I deal with not being able to talk to Citadel? What if I get a network partition and I can't get new certs? So there's a couple options. So today you fail, right? That's what happens. Is that after your certs expire and you can't go get new certs, you cannot establish new connections. You can continue to use your currently established connections, and if you have long-lived connections, that may be okay. But yes, you will not be able to establish new connections. And that is a desirable or not consequence of the system. There are a couple different options that we are looking at enabling. So one of them is grace periods. So allow a cert that expired 5 minutes ago. That's okay, right? We can be a little wishy-washy with the exact expiry. That's one strategy. That only buys you a little bit of time. That doesn't solve a partition issue. The other thing is that Citadel itself is a stateless service that can be run horizontally scaled, right? So you can run more Citadels. There are some security posture problems with that, in that it is handling key material, so you probably want it to run in the secure zone that's safer than, like not in the DMZ, for example. And so if you have a partition between DMZ and your production or your secure zone, you're still out of luck, right? And And then really, yeah, so it is an outage, and that is a desirable property of the system. It's not desirable, but it is a direct property of how the system behaves, right? You're not partition tolerant if you're on the wrong side of a partition from Citadel.
The 5-minute thing is a used concept in other areas.
Exactly.
IPsec has
Exactly.
time.
Exactly. Yeah, and so it's very likely that that is what Istio will ship as a tool to start to mitigate that. But today it is just the hard deadline.
Is it hard to revoke a service?
Yeah, so this is the key, and I didn't talk about this, I'm sorry. So this is the reason that we issue short-lived certificates, is that it makes revocation lists easy to manage, right? So if a cert lives for a year, then I have to keep it on the revocation list for probably a lot longer than a year. If a cert lives for an hour, I probably don't even need a revocation list, right? And so we don't maintain revocation lists now, at least not in Istio actively. You could if you wanted to, and that is actually the single biggest advantage of these ephemeral certificates, is that revocation is arguably the most painful part of cert management, and that you really can largely ignore.
So you take the risk.
Yes. And you can't, to be clear, this would still work. You can still publish certs in the revocation list, but you can only need them there for a lot shorter time.
Attack surface is reduced to.
Exactly, exactly.
And I think kind of similar with the draw, right? You don't put it in the draw either.
Sorry, what was the question?
I think this is kind of very similar, to the draw talk.
Mhm.
Long.
Exactly, yeah. So similar to JOTS, right? It's the same principle that underpins JOTS, which is we want short-lived credentials, right? So you have to go refresh.
Is the node agent coupled to kube, or is it a standalone process that you run on Citadel via?
Yeah, so today in implementation, it is to some degree coupled to kube, not heavily. But yes, in principle, that is a thing that you can run anywhere, right?
And it's just an implementation of the workload API? Or?
It is not the so Spiffy defines a workload API, which is the API that is supposed to be presented on a node to a workload requesting a certificate, right? And so Spiffy defines what that API looks like. No, it is not the workload API. It is a spiritually similar API that is not verbatim the workload API, but it's very similar.
How does a node agent differ from like node authorizer at the Kubernetes level?
So I'm a little fuzzy on node authorizer, but my understanding is that node authorizer verifies that a node is valid to run workloads in Kubernetes, right?
These are also like restrict permissions based on like the certificate issued for that node. So it can only access resources that are running on that node.
Oh, interesting. So I'm actually not familiar with how the node authorizer works to be able to answer your question.
I was going to say, we do use the node authorizer, and like I agree with you. It sounds they're doing a very similar job.
Okay.
The node authorizer requires that each node have its own identity,
Mm-hmm.
and so basically you need to bootstrap
Interesting. Okay.
self-cert onto the node.
Oh, okay. Gotcha. So this.
Per node identity.
Yep. Yep.
So like it's kind of a similar thing.
Totally.
You need
So-
per node identity for
Yes.
Citadel, but I don't think it's sufficient.
Totally. So, and so this may be where the overlap exists, is that I didn't talk about how we bootstrap the node agent itself. This is a critical piece of the security puzzle, is that node agent bootstrapping, and that traditionally relies on certs that are only available on a node, right? So the AWS node certs, GCP has the same. You might use an HSM on a bare metal deployment, or if you are provisioning node identities, that could be sufficient.
For JOTS with the token, with RJOTS we can specify policies to verify them. Is there a component in Istio to also issue them?
Yeah, so no. Today there is not JOT issuance in Istio. I believe, where is Lizan? Is not, excuse me, sorry. Lizan is not in the room. So I'll point you to somebody to ask. I know that Citadel is growing the ability to do JOTs, is my understanding, but I don't know the current state of that just offhand.
One more is the Citadel can connect to external CA.
Yeah, so today there are a limited number of integrations with Citadel that are done in process in Go. The big one being Vault, so it can go talk to an existing Vault instance to go grab certs. One of the problem points with Citadel is that it lacks some of the extensibility that other pieces of Istio have. So it does not yet have a good set of APIs for talking to other cert infrastructure. One of the ways that we want to fix this is implement ACME in Citadel. So ACME is an automatic certificate issuance protocol. And if you've ever used Let's Encrypt to go get an HTTP certificate, those people are the people that developed ACME, the certificate management infrastructure. And it's a protocol that allows you to go and get certificates from a trusted source and prove your identity to that source in a way that it can authenticate and verify, right? And so that would be the most natural extension to Citadel. And then over time, we'll start to see other things like Vidify or other kind of well-known large PKIs. I think we'll start to see integrations in Citadel there.
Small one now. So the node agent currently with Kubernetes implementation, how does that actually run? Do you just run the kube set or something?
Yeah, exactly. So in Kube, the node agent runs as a daemon set.
Yeah, okay. And the Unix domain socket, how does that expose what you just created in domain socket and on the
Yep, yep. So that's part of the injection. Is if you have, so part of the injection of the Envoy container includes that mountain point. All right, any other questions? All right, awesome, thank you. This was excellent. Y'all had phenomenal questions. This was really good.